Welcome everyone to the last day of the conference, and thanks for obliging to start at 9. So great to see you all here. So our first chair of the session is Tuhin. So just please take it away, and the first talk is remote.
Good morning, everyone. Welcome you all to the last day of the conference. So today's main theme is next generation experiments. So there will be two talks in the first session of 30 minutes each. So it's like 25 minutes for the talk and 5 minutes for the question. So the first talk is by Jack Burns. He will talk about the frontiers in 21 centimeter cosmology from the far side of the moon.
Very good. Thank you. Thank you for the invitation to speak with you today about 21 centimeter cosmology from the far side of the moon. Much of what I'm going to speak about today is really facilitated by NASA's new Commercial Lunar Payload Services program, which are commercial landers that carry scientific payloads to the surface of the moon. The image that you see here is an artist's concept of the Intuitive Machines lander, which will carry our Rolls' radio science payload to the surface of the moon, particularly to the South Pole, by the middle of this year. That will be followed a couple years later by Lucy, which is going to the far side of the moon and will operate at night. And both of these are enabling of then future interferometers that for the far side, which I will tell you a little bit about as well. Some of this material, this overview, is published earlier in Planetary Sciences Journal for those that want to look at that a little bit further. So let me start off by just acknowledging my NASA-funded team called the Network for Exploration in Space Science, who played a key role in much of what we're talking about. In particular, I want to acknowledge our students, are both graduate students and undergraduate students, who do play such a vital role in much of the work I'm going to be talking about this morning. So let's get right into it, talk about the lunar far side. It's been known for 60 years before Apollo 11 landed on the surface of the moon. There were ideas circulated about doing radio astronomy from the far side of the moon. And the reason is that the far side is uniquely radio quiet in the inner solar system. That 2,000 kilometers of rock between the far side and the view of the Earth really eliminates any noise coming from the Earth. And you see this verified from the NASA RAE-2 satellite, which flew in the early 1970s. This is relative antenna temperature versus time. Noisy is when the spacecraft was above the in orbit above the near side, and then dramatically quieter behind the far side. Secondly, the moon lacks a significant ionosphere, particularly at the frequencies involved in 21 centimeter cosmology. And that's important because in contrast to the Earth, where refraction and absorption play a key role in limiting and producing systematics for observations. And then finally, maybe not recognized as importantly, but indeed it is the fact that the lunar surface is dry and stable because the radio beam does couple with the dielectric in the subsurface. But in contrast to the Earth, where, for example, moisture can vary from day to day and change the that coupling and complicate the beam, the moon is very stable. So when the question is, why has it taken so long then to begin such observations from the moon? Well, I'm going to argue there are two reasons. First is science. Up until about a decade ago, we really lacked compelling science that uniquely required the far side of the moon. Those have emerged. One of those cases is the magnetospheres and space environments of habitable planets. Earth-like planets that have magnetic fields will radiate low-frequency auroral kilometric radiation, and that could be very important in trying to understand the habitability of these planets. I'm not going to talk much about that today. Instead, with this conference, I'm going to focus more on the unexplored dark ages and cosmic dawn as the other major science case. The second reason I will argue that's taken us a while to begin these observations is the lack of access to the moon. It's been 50 years since NASA has last landed on the moon, and only recently have we seen some landers such as the Chinese Chang'e missions. And also recently, NASA has begun returning to the moon with the new Artemis program, the SLS rocket, and the Orion crew vehicle, which had a successful mission. And by the middle of the decade, NASA is expecting to land the first woman and the first person of color on the surface. At the same time, NASA's Science Mission Directorate has established this commercial lunar payload services program to bring science payloads to the surface of the moon with regular deliveries. So just a little bit about what this CLIPS program is. It's intended to be rapid acquisition and rapid delivery using commercial landers to carry NASA-funded payloads. There's going to be 3 of these CLIPS that are scheduled to land on the moon later this year. The first by Astrobotic, and then also Intuitive Machines out of Houston, Texas, is going to land 2 landers later this year, including our Rolls' radio science experiment. So what is Rolls'? Well, it's an acronym that you see here with the red letters, and it's intended to begin helping us to understand the surface environment of the moon. And you see in the upper left is that same cartoon picture showing 2 of our dipole antennas. There's 2 pair of antennas, 4 monopoles, 2.5 meters in length each. Our instrument team was originally led by Bob McDowell, who is retired in this last year, and Nat Gopalswamy is now the acting PI. Bill Farrell and I are 2 of the lead scientists. You can see here a little bit more about the antennas. These are called stacer antennas, or hollow tube antennas that are spring-loaded and just pop open, very high reliability. And at the core of this Rolls package is our spectrometer board, which is based on the NASA SMAP, Earth Remote Sensing Satellite, and it operates over 2 bands ranging from 10 kilohertz up to 30 megahertz. Let me just show you a brief video now from Intuitive Machines on what we hope this landing is going to look like in late June.
Acquisition of signal and lunar orbit insertion complete.
HDA scanning in progress. Safe sites found.
Prepare for landing.
Now, of course, we have our fingers crossed that the landing is going to be this smooth, but we already know landing on the moon is not easy. There's been experiences, for example, with the Chandrayaan spacecraft a year or so ago. And as we said, NASA and US has not landed on the moon in 50 years. So we're proceeding cautiously, but optimistically. Our landing site that was established in conjunction with NASA is near the South Pole. If the Shackleton crater that you see down here is more or less the South Pole, we're about 10 degrees away on the rim of a small crater called Malaparte A. It's a good landing site, pretty smooth, and has some real advantages for a first mission. The science goals of Rolls, as I mentioned before, is really to get a handle on the lunar surface environment for doing radio astronomy. So that includes measuring the electron sheath, which is has not previously been measured but believed to exist on the surface, using the electron plasma frequency down at frequencies below a megahertz. Also demonstrate the detection of solar, planetary, and other radio emission, to map the galactic spectrum, which is poorly known below 30 megahertz. That's very important for 21 centimeter cosmology, because that's the foreground we're going to be looking at. Here's an example of the kind of data that we expect. These are observations from the NASA Wind Waves experiment, which is currently at Earth-Sun L1 Lagrange point. This is a dynamic spectrum. This is frequency going from about 14 megahertz to about 10 kilohertz versus time. And you can see the richness of the radio emission. In fact, this makes a good case of why you want to be on the far side of the moon, because much of this radio emission is blocked off when you're behind the moon. You can see, for example, horizontal stripes. That's RFI emission coming from the Earth. There's radio emission from Jupiter. There is the Sun, type 3 and type 2 solar bursts that you see here. And then, of course, the Earth itself, as I mentioned before, is a strong source below about a half a megahertz of auroral kilometric radiation. This actually makes the Earth a good candidate to view as a kind of exoplanet in preparation for future radio interferometry observations of nearby exoplanets from the lunar far side. All right, with that said, let me also talk a little bit about one of our goals in preparation of 21 centimeter cosmology is to understand the interaction, the electromagnetic coupling of the radio beam with the subsurface. And here we can see some modeling done by my colleague Bagnon at NRAO using the CST Microwave Studio software. This is power in the radio beam versus angle that you're looking at here, where 0 is the zenith. And two examples. One is the lander plus the radio antennas as they would be in a vacuum. And then secondly, on a layered regolith. And you can see there's a distinct shaping of the radio beam as a result of that interaction. So our effort in this first mission is to measure that interaction using some forward modeling techniques that I'll tell you a little bit more about, and get a handle on what that subsurface dielectric constant is in preparation for subsequent missions. The instrument parameters for ROLSA shown here in more detail, along with some very recent pictures showing the integration of payload packages onto panels that are on the side of the spacecraft, as well as another example of our deployable antenna, our stacer antenna that you see over here. Well, these pictures were taken last year when I visited Intuitive Machines in Houston. This gives you an idea on the left-hand side, the size of the lander, and then on the right side is the new control room built by Intuitive Machines. I hope to be at that control room in late June for the landing of our payload there. So let me move on to talk about the second scheduled and funded mission to the moon, the Lunar Surfaces Electromagnetics Experiment, or LUCI for short. This is going to the far side of the moon. It's led by my colleague Stuart Bale, who's the PI for NASA, and also Angie Slozar, who is the representative from the Department of Energy, who is working with us on this. Stuart recently posted a short paper on LUCI, which you can look up on the archive. So LUCI, or LUCI Nights, as we refer to it, because we will be operating through the night, has these 4 stacer antennas, or 6-meter tip-to-tip antennas in this case, a 4-channel receiver going from 1 to at least 50, and possibly to 100 megahertz. We're still working that through. We're also, we've placed this antenna on a turntable so we can spin it when a far field calibration source, which is funded to be in orbit of the moon, will pass by, so we can map the radio beam, which is important for us to have a determination on for cosmology. The lander itself, when it lands on the surface of the moon, it will turn off, so it'll eliminate any electromagnetic interference from the lander, and all of the noise characteristics can be determined by our instrument, which we worked hard to understand. Here you see a little bit more of a close-up of the top bay that will be on the lander with the antennas, our electronics box, our batteries, and then also looking at a distribution of our spectrometer antennas and comms in this chart that you see over on the right. So what is the goal of Lucy? Lucy Night is a radio cosmology pathfinder experiment. It's going to operate in that band that is expected for the dark ages and some of the cosmic dawn. That is the discovery area for cosmology, as indicated by the U.S. Astrophysics Decadal Survey, published about 2 years ago now. And you get a handle on this, as was discussed earlier in this conference, on what we are expecting here. This is the Big Bang over to the left, and today's universe on the right. It's logarithmic in time. And of course, we begin with the CMB, and coming out of the epoch of reionization is a universe literally filled with neutral hydrogen that emits a 21 centimeter signal. This is called the cosmic dark ages because, of course, there are no other sources of compact radiation at this time. A little bit later in the evolution, of course, before stars turn on, that's the beginning of cosmic dawn. JWST and the Hubble Space Telescope can stick their toe into the waters of the late epochs of the cosmic dawn, but doing 21 centimeter cosmology will allow us to probe the very earliest stages of cosmic dawn, and then, of course, the dark ages. There are two ways to probe it. One is using the so-called global signal. Think of this as an analogy of the CMB blackbody spectrum that was originally mapped in great detail by Kobe. And the second, that I'll speak a little bit more about later, is using an interferometer to look at spatial fluctuations from the power spectrum. The core signal, of course, is from neutral hydrogen. It's the 21 centimeter spin flip transition. And in the lower right here are some example models of what we expect the global signal to look like. This is the brightness temperature measured against the radio background versus frequency. And also it's redshift because we're scanning here a series of different time periods. Unlike the CMB, which is limited to a narrow slice of the universe, here we can actually look at the evolution of structure from time periods running from redshifts of 6 to greater than 100. Here you see various models. The dash is an example of a standard lambda CDM cosmology and standard star formation. You see two dips in the spectrum, one here in the dark ages, which is just due to adiabatic cooling, and the second is a absorption trough, which is caused by star formation when Lyman alpha from the first stars couple with the spin flip transition through the Voigt House and field effect that was also discussed earlier in the conference. And then later here, X-ray heating also affects the shape of the signal. Now, of course, a couple years ago, the Edges experiment reported this gray absorption trough in here as a possible 21 centimeter signal from the cosmic dawn. This has been very controversial, in part because it's much lower in absorption than any of the models we're expecting. This could, of course, mean interesting new physics, such as cooling, interaction with partially charged dark matter. But it can also mean that there is significant systematics which has produced this, because the Ceres-3 experiment did not confirm this signal. This is all the more reason why taking a fresh look at this global signal from a new and more pristine environment on the surface of the moon. That's really a major goal of Lucy. But of course, even from the moon, this is a tough experiment. And the reason is we have to look through a foreground that's 4 to 6 orders of magnitude brighter than the signal. The signal in red here looks a little funky compared to what I showed you before because this is logarithmic in brightness temperature. But this foreground is also has a spatial variation, so it's going to be time variable. And we're also looking at with a beam that has a frequency. So removing that foreground is not at all straightforward. Our group at the University of Colorado, led by David Rapetti, myself, and our students, have been working for the last decade on developing a Bayesian inference forward modeling data analysis pipeline, which we believe is equally important to the actual instrument itself in being able to pull out such a signal. So what does this pipeline look like? Well, in the schematic, we use modeling or training sets. We're not using machine learning. We're using pattern recognition to identify. And our training sets include beam-weighted foregrounds and all the Stokes parameters. The signal also includes the receiver. And then we use singular value decomposition to produce a set of eigenmodes to basically linearize the problem. And we use information or Bayesian evidence to determine the number of modes that are best used to then fit the signal. And then finally, nested sampling to pull out the physical parameters, such as the time when the first stars turn on in a cosmic dawn, or even parameterize some of the dark matter models. So we have a series of papers on this that I won't go through, but to simply note that all of these pipeline codes are now publicly available on GitHub. All right, well, quickly on the path forward from here, I've talked about Rolls', talked about Lucy Knight. What comes next after that? Well, those are interferometers, such as what Leon Koopsman talked about a little bit earlier. This is our version of a radio interferometer called Farside that we've done some design work in conjunction with JPL. These is a tether deployed antennas. These are thin wire antennas that are inside these tethers that are deployed using these single axle rovers that you see here. So this is the beginning of being able to do a power spectrum and looking at the 3D spatial structure in the 21 centimeter signal. It's very powerful because it opens up not only a probing of cosmology, but also additional physics, dark matter decay, and annihilation can affect both the global signal as well as the power spectrum. I've already talked about non-gravitational interaction of dark matter with baryons. And then a student of mine, Joshua Hibbert, and our group published a paper this last year looking at warm dark matter and its impact on the 21 centimeter signal. Here you see a couple of examples, the difference between cold dark matter and warm dark matter. Warm dark matter has more streaming out of the filaments and produces fewer halos around galaxies, which solves one of the leading problems for CDM. It also is it's a literal playground of to explore physics beyond the standard models and cosmology, because there's such a large number of linear modes that are still available, certainly in comparison to C and D. So we can look at scale dependence, the primordial fluctuations, deviations from Gaussian statistics, primordial gravitational waves, insight into inflationary phase, just a wealth of new physics. But to do this, we really need a large
Jack?
array. We need an array
Hello.
with at least...
Jack,
Yes.
we have 2 minutes left.
Yes, we need an array with at least 100,000 dipole antennas. And let me show you just a very brief video of a concept for such a large array called FarView that also manufactures antennas on the surface of the Moon.
FarView is a next-generation astrophysics radio observatory built on the moon's far side. The only radio-quiet place within the inner solar system to study the earliest stages of evolution of the universe. The Lunar Observatory will be built from lunar resources and constructed directly on the surface of the moon using space industrial equipment sent from Earth. The required materials will be extracted by Lunar Resources Manufacturing Technologies from the lunar regolith. A truck rover then delivers the extracted raw metals to the construction site for the fabrication of antenna elements, solar cells, electrical transmission cables, and batteries. The observatory's antenna array and power grid is then assembled directly onto the surface of the moon, utilizing Lunar Resources Space Manufacturing Technologies and its partners' intelligent lunar rovers. FarView is estimated to be a 10 by 10 kilometer observatory with 100,000 dipole antennas and will take less than 4 years to be constructed. The Lunar Observatory will explore the origins of the first structures in the universe, opening new science windows into low-frequency radio astronomy, seeking to uncover new physics and test standard cosmological models, and enable new science in heliophysics and planetary science. FarView will be one of the most powerful radio observatories for learning about our universe.
So let me just summarize by saying that this is what I try to present today is an evolutionary roadmap for the development of radio astronomy and cosmology on the moon, beginning modestly with these single instruments, these single antennas with Bose and Lucy, and then evolving over time into the 2030s with these large arrays. So let me stop there. I'm happy to take some questions.
Thanks, Jack, for giving a nice overview talk. It's time for questions.
Hi, Jack. This is Leon. So very nice and very impressive talk and vision on the future. So my question is on the Farsight mission. Of something that we are worrying about is, of course, when we place these dipoles and receivers on the moon, especially if you do very large areas, it's very hard to know where we actually place them, right? Both in X and Y and in Z. So have you thought about this, how to sort of calibrate this or measure the positional accuracy of the receivers on the moon? Or do you assume some uncertainties on their placements?
Well, Leon, good to talk with you. You've struggled with exactly the same problem that we thought about. One of the ways around this is having a radio beacon, which is in orbit of the moon, as well as what will be an establishment of some GPS-like systems, I think, over the next few years. This may be helpful in determining the positioning of the individual antennas. So this is definitely a work in progress at this point. We have not settled on any one solution.
And maybe just a short follow-up question, and maybe I missed it. So you do still use a traditional correlator technique. So we were thinking more in the direction of an FFT type telescope, because that reduces, of course, the correlator capacity drastically, and therefore the power consumption. So I don't know how you're going to approach this.
Well, so far what we've looked at for Farsight is using an FX kind of correlator, so kind of a traditional approach. But I think part of the reason that we're looking forward to collaborating with you all is to look at what may be the best approach to do.
Okay, thanks, Jack.
Hi, Jack. This is Mayuri. Thanks for that great talk. I was wondering what kind of model has gone in for the lunar regolith when you design antennas to be placed as landers on the lunar far side?
Yeah, that's a great question, and it's something we would like to know more of, but we've been using data from the Lunar Reconnaissance Orbiter as well as the gravitational mapping that was done a few years ago to get a handle on the structure as well as estimating. Also from Apollo, there's some data on the regolith. So we've been using those as priors to our forward modeling, and then build up a data set from that that we'll test with Rolls's and Lucy.
Hi, it's Matt Dobbs here. The question is specifically for Lucy. It's great that the permeability of the lunar surface isn't changing, so that you don't have to track it and take that into account. I guess you do need to measure it at least once, very accurately below that experiment. How do you do that?
Yeah, that's a great question. That's a tough one, and we can't with Lucy measure it very accurately. We have to infer it from the plan is to use sources such as Jupiter to be basically passively sound the subsurface and then measure the resulting response that we see to infer the properties of the subsurface. This is obviously not ideal. We do have a second instrument, though, that we proposed to NASA recently that would land a 2-element interferometer near Lucy and then drive it to the Lucy site and do interferometric sounding using an active sounder to measure the dielectric properties. So that is a proposal that we have submitted to NASA.
Great, thank you. When is the planned launch for Lucy?
That's late 2025, early 2026.
Great, thank you.
No more question. We can thank Jack again. And
Thank you all.
thanks, Jack. The next talk is by Mayuri. So she will talk about Patyush, a space-based 21 centimeter experiment.
Okay, thanks everyone. And I'm really glad that Jack went before me because he's done a lot of the groundwork and he's kind of presented the dream. So I'll take you through one of the experiments that we have been working on right here at RRI called Patyush, and I'll come to that in a bit. So before I move on, here is a snapshot of some of the members who have been actively involved in the Patyush experiment, and several others that I couldn't list here, including a lot of support that we get here at RRI from the electronics and mechanical engineering services, several students who come through the lab, so a big shout out to them. So this is the signal we have been talking about quite a bit during this conference, but just a quick introduction. What we're looking for with Patyush is the monopole signal, and we're specifically talking about cosmic dawn and epoch of reionization, not right now thinking about the dark ages signal. So this is like a kind of non-comprehensive forest of signals we could expect just from the standard models. And so just to give you an idea that the parameter space is quite wide open. So this is my own kind of a toy model to motivate going to space and to the lunar far side, and I'll come to that. And Jack gave his kind of version of this slide, so I'll just walk you through mine. So there are several reasons why this signal has not yet been detected, and it's not just the thermal noise, because if you just look at an ideal instrument and the signal strength from most standard models, and again with the caveat that you're able to do a good job separating foregrounds, there is no reason why this should be a hard experiment, but clearly we have not found the signal. And just from a systematics perspective, this is a not comprehensive list of challenges that we face in the lab on the field on a daily basis. So some of these are how the antenna properties change based on the environment in which it is observing, which can be time variable depending upon where you observe. There are challenges that come from radio frequency interference, not just the ones that come from the external environment, for example, FM transmitters that are right in the middle of our band, but also from our own electronics. You could have challenges that come to the data analysis methods, which could introduce artifacts, the way you propagate errors down your pipeline. And so basically there are several challenges that I've listed here. But I'd like you to kind of pay attention to the ones listed, highlighted in blue, which we believe are challenges that are unique to observing on Earth, whether you observe in land or water, but basically on Earth, and which is starting with, based on who you ask, there are effects that you could be seeing to 1 part in million due to the ionosphere that could introduce chromaticity in your signal, which is a big challenge from separating the signal from foregrounds. You could have, again, of course, you have radio frequency interference. You could go to very remote radio quiet sites. I'll come to that in a bit. And of course, one of the challenges that we think is probably the most critical or the current active bottleneck is understanding your antenna in specific and what it does and how it behaves over a wide range of frequencies and how it couples to the terrain around it. That could be the soil below, it could be things in the horizon. So these three can be alleviated to a large extent if you go to the lunar far side and in space, so as an orbiter. And that has motivated us to propose an experiment to the Indian Space Research Organization ISRO, which is called Pratyush. And just for a fun twist, Pratyush is a take on Pratyush, which in several Indian languages means the dawn or sun, which is a nice connection. And Pratyush, in its final vision, will operate from 40 to 200 megahertz and will be a lunar orbiter operating and making scientific measurements when on the lunar far side and transmitting data back to Earth when on the near side. Here I must acknowledge a lot of the groundwork that has been done by Jack and his colleagues and proposed a mission called DARE. So Pratyush has taken some inspiration from the DARE in its concept, but we have taken our own track and diverged in terms of the specifics of how we design our antenna, how we calibrate, and so on. So the baseline design that I'll present you today operates over a 1 octave region focusing on the cosmic dawn, which goes from 55 to 110 megahertz. And the lunar orbiter will be custom designed for the primary science goal of trying to detect this signal from the cosmic dawn. So the ground-based counterpart experiment, which is right here at RRI, it comes in the form of Saras, which is very mature, and Saurabh did a great job of presenting all the fantastic results we've been getting from Saras. But there'll be some unique design features that come to Pratyush because of the way it will operate in space. Pratyush has currently been funded for seed studies, so it's like a preliminary design studies by ISRO since 2019. And the current status is that we have a laboratory model that is being tested in various phases. And we propose to fly Pratyush in 2 phases. The first phase will hopefully fly around Earth, orbit Earth, and make some preliminary science measurements and also alleviate a lot of the technological risk because we are coming up with several new things that are kind of pushing the boundaries. And the second phase will be a lunar orbiter. So I won't get into this in great detail, but this is just a slide to motivate that there is good reason to believe from previous experiments and modeling that the lunar far side is expected to be extremely radio quiet, and there's good reason we want to go there. And this is just a nice cartoon image showing what we want to do with Pratyush and make observations when we are on the far side of the moon and in the radio quiet zone of both the sun and the Earth. So this is what Pratyush looks like in its current avatar, which is we have a monopole antenna, much like the Saras experiment, but with some modifications. We have a cone which sits on top of a profile antenna reflector. So this entire gray structure you see here is a custom designed antenna which has extremely custom design properties, including how it behaves over the entire frequency band of 55 to 110 megahertz, and a lot of detail has gone into the beam and the return loss of this antenna. And sitting right beneath this will be the satellite or the craft or the bus. So the way we envision Pratyush to operate is that it will be its own dedicated mini satellite. So this is not like a payload experiment on a bigger satellite with other experiments. We want to stay clean in terms of also RFI and interaction with other experiments. So this will be its own entire mini satellite. And in this satellite, in this bus, we will have the analog and digital electronics of Pratyush as well as the spacecraft electronics. So I'll walk you through each of these very quickly. So this is what it looks like right now in the lab, and those who are interested can walk in and we can have a chat. So this again, like I mentioned, the essential basic structure of Pratyush is the following. We have an antenna, which is a monocone antenna on a shaped reflector that operates over 55 to 110 megahertz. We have some analog electronics, which currently uses commercial components. And this includes the purposes of calibrating the bandpass of the receiver, as well as calibrating the S11 of the antenna and measuring the S11 of the antenna in situ. And we have the digital electronics, which performs the function of sampling the data that comes in from the analog receiver, as well as doing some preliminary processing before we send it to the satellite bus, from which we will be getting the data to the ground. So quickly walking over the antenna aspect of it, like I mentioned, we have taken a lot of care in how we design the antenna, keeping in mind the property of smoothness that Saurabh had referred to during his talk. So just to give a summary, the design philosophy or the approach we have taken with Saras as well as now Pratush is that we want to introduce as minimal number of spectral richness in our data set as possible from the instrument, and this includes paying attention to how the antenna couples the signal from the sky into the receiver. So you want your beam to be reasonably achromatic over the entire frequency range, as well as not have a lot of richness or features in the antenna return loss, which is effectively the coupling function of the antenna to the receiver. And of course, it's really hard to put hard limits on this. So what we do instead is we have our own signal analysis and forward modeling pipeline, where we put in a model of the foreground from some physically motivated sky model. We introduce the antenna beam as well as return loss over the entire frequency range, and we add various signals from the standard models into this pipeline and run it through how it comes out on the other side of antenna. Effectively, you might see something like this. And now when you kind of fit it with these smooth functions that we refer to and correct for some of the antenna properties which we have designed for, we want to be able to recover the signal in processing. So that's the approach, and we went through several iterations of this. And I want to highlight one specific point here is that when you design an antenna for this experiment, you have to co-design it with the bus on which the antenna is going to sit. Because if you have a chunk of metal, basically the satellite, on right in beneath the antenna, that chunk of metal is bound to influence the properties of the antenna. So you could design this gray stuff in free space without anything else, but when you put a bus beneath it, it changes. So we have to do this, we have to co-design. So for now, we have assumed a CubeSat model, a large CubeSat, whose dimensions are standard, and we have gone ahead and we have converged on this as the baseline design. But this can, and we expect this to iterate and change a little bit once we get into the final stages and start talking to ISRO about the details of the bus. So this is a snapshot of the analog electronics in the lab, and this is some details of the architecture that I won't get into. But it suffices to say that in addition to the bandpass calibration, which is now reasonably well established in our lab from all the expertise that we have over the several years, we have decided to include another section in Pratush, which does the in situ measurement of the antenna return loss. This is because we do expect that the antenna properties are bound to change when in orbit, especially due to any properties of the antenna changing when you see the sun for some time and you don't see the sun for some time. So over a period of 2 years, which is what we expect the mission lifetime to be, you expect the mechanical properties of the antenna to change within certain limits, and this is definitely going to end up changing the properties of the antenna electrically as well, which is what we care about a lot. So there is a function to do an in situ coarse calibration or measurement of the antenna return loss. And this is a snapshot of the digital electronics. We have kind of started, we have done this quite well on the ground with the very latest generation of FPGAs, and we're continuing to move ahead. But for Pratush, we have to keep in mind also the kind of availability of space qualified boards and electronics. So that has been an important challenge for us. And furthermore, we realize that on ground, you can take the liberties of passing on data rates at using gig Ethernet, which is not something you can take for granted in space. So we do take care of that, and we have kind of included a lot of processing electronics in the lab model right now with just a small Raspberry Pi to kind of get this data processed to an extent enough that you're able to send it to the satellite and then to ground. So just to give you a sense of scale and some of the measurements we've been doing, this is Ibrahim, who is leading our workshop activities, and like average human length scale. So this is how big Pratyush can be. So you can imagine that this is quite large for an antenna that you can imagine flying in space. It's not a little thing that you send off on a CubeSat. And this just comes from the wavelengths we're talking about. And here are some more measurements that we've been doing here at RRI. So measuring antenna properties in the lawn. And clearly we do see the effect of the soil itself in shifting some of the kind of return loss amplitudes, because that day I think it had rained, so we have a more conductive soil. But these things, of course, are something we have been looking at for quite a while. And yeah, so we have been doing some testing of the analog receiver. This is all extremely miniaturized compared to most of our ground-based efforts. And we are kind of getting to the levels of smoothness and calibration that we have been kind of designing for. Again, data rates, we've been finding some interesting bottlenecks in how far you can push a Raspberry Pi. And we have now like pipelines and codes that can correct and flag for some of these data rate losses. But yeah, this is just to show you some work in progress. And an interesting problem that I will come to is that on ground, you have the advantage of separating your electronics that can be extremely noisy from your antenna, which is picking up this extremely weak signal by 100 meters or more. But you can't do this in space for just practical reasons. So we've kind of decided to face the problem head on and say we're just going to put everything right next to each other, know what the devil is that we're going to deal with, but we have to figure out how we kind of suppress all of this noise that your electronics generates. And we've been doing some interesting experiments working with a vendor who's developing materials and methods to provide a box or an EMI shield, electromagnetic interference shield, which can be extremely lightweight. So these are just some tests, and you can see we've done some ad hoc setup to make these measurements, but I can assure you that they work. So again, some of these are preliminary, which is investigating the kinds of orbits we can explore in space, and a lot of these efforts have been led by students. So this is, I can talk to you in more detail about this. I think I might be running out of time. And we are very aware that one of the big challenges we will face, in addition to this EMI shielding problem, is the thermal swings that our antenna will experience when going in and out of the sun line when on the lunar far side, especially in the lunar orbiter. So we've been doing some thermal simulations. This work has been mainly led by Surya, who's a student who's in the audience. Some more pictures of that. We're trying to understand this still. But here I'd like to take a small pivot and say that there is definite advantage in going to the lunar far side as an orbiter. But like I said, in phase one, ideally we want to kind of just be orbiting the Earth, partly for risk mitigation and figure out what is it that we want to do in space, in the lunar far side in terms of technology. But we do believe that if we observe over a relatively radio quiet region on Earth, in space, for example, over an ocean, we could be making some significant signs by cross-correlating with a counterpart ground-based experiment like Saras, which uses the same design philosophy, but you're just observing in two completely different environments. So here shown in blue are the kinds of signals we think we can detect in Earth orbit, and in red and blue together is the entire forest we think we can catch from the lunar far side. So taking a lead on this, it's important for us to understand, I'll just skip this slide. It's important for us to understand what the RFI environment is on in orbit around Earth, because when you go higher up, of course, you're getting further away from all these FM transmitters you want to get away from, but you're also seeing more number of them. So Sonia here has led an effort called Starfire, and that paper is out on archive and hopefully will soon be published. We are close, we think. That kind of takes a limited database of FM transmitters publicly available from around the world, and this can be populated even more, and we're kind of working on that. And we can generate all kinds of things like RFI spectra at various altitudes above Earth or a specific location, generating heat maps like this over the entire globe. And this is a pipeline we have in place, and we will be using this to kind of understand what kind of orbits we want around Earth. I've gone over this, so this is an important R&D problem we're working on, which is this EMI shielding.
So while I have the mic, I'll quickly kind of throw light on another next generation experiment that we are working on right here at RRI. Jens on the first day gave a talk on the CMB spectral distortions, and specifically this is the kind of spectral distortion we can expect from the primordial recombination lines over the epoch of recombination. So here at RRI we have made a humble but sure beginning to try and go after the primordial recombination lines that can be detected from ground. And this comes in the frequency range of about 2 to 4 gigahertz, where we expect the signal to noise ratio to peak. And we have done some feasibility studies. It's going to be a large and challenging experiment, but we think it is possible. So this is what the signal looks like over 2 to 4 gigahertz. And you might note that the temperature range here is tens of nanokelvin. And here we are trying to detect the EOR signal, which is 100 millikelvin. But one thing I can tell you that this signal does have going for it is that it is very, very well known. So then we can get into this philosophical argument as if it is supposed to be so well predicted, why go after it? We can chat over coffee. But let's say we want to detect this signal. We are messed around by systematics at this level, a little lesser in the sense that if I know exactly what I'm looking for, it is easier to find it. And that's the philosophy we're taking. And we have been doing some nice, interesting antenna designs led again by students and RAs here. This, for example, is a unique antenna designed explicitly to have these properties of achromaticity and beam and return loss smoothness, led by Kavita. I think she is maybe here as well. And this is for scale. I can hold the entire antenna up in my hand, so it's that big an antenna. But clearly for a full confidence, high confidence detection, we have to scale these. We should have an array of hundreds of these. And we're working on that problem right now of scalability, led by Kavita and Arun. And so all these simulations and feasibility studies have assumed an ideal instrument, which we know does not happen in practice. So we have started kind of introducing non-idealities in the instrument to understand how much of the non-ideality you can allow. And I won't say much about this because Darshan has a poster right outside that door, and you can chat with him. I think he'll present soon. And we believe that you don't have to have an ideal instrument. You can make a detection with some non-idealities, again hinging on this fact that you know what the signal looks like. So even if you mess it up, you know how you're messing it up. So again, here are some interesting antenna designs. This is another student, Arun, and again, he's led by me and Kirti. And yeah, so I'll stop here. And I didn't get my warning, so maybe I'm under, I don't know. So yeah, the summary is that we are going to make a fly an experiment called Pratush. Hopefully we will be selected for project mode. We are not quite there yet, but we are in the works. And the idea is to detect the global 21 centimeter signal from space, starting with an Earth orbiter and then a lunar orbiter, cooperating with Saras on the ground. And Apsara is another experiment that will operate over 2 to 4 gigahertz and is in the first step of one prototype element, and we're working on that now. I'll stop there. Thanks. Yeah, okay. I went fast.
Thanks for the very nice summary. I had a quick question, maybe I didn't follow. There was a plot you showed of a noise spectrum in nanokelvin. Was it not? So then that's amazing, right? Or, I mean, am I missing something? Like you said, there is something in the spectrum which is not still understood, or?
Sorry. So this is the predicted signal, the additive distortion to the CMB that comes from the epoch of recombination. And you can think of each of these peaks as one hydrogen transition line. So it could be like principal shell number 12 to 11, 11 to 10. And that's smeared out by how long it takes for this state to settle. So that is what the signal is. And the baseline that gets added to this is the CMB itself. So I've removed the CMB as a black body. And this is what I would expect as the signal from recombination.
Yeah. So then it's challenging. Yeah.
Yeah.
Thanks.
Okay. All right. I was waiting for someone. So, question on this plot as well. So yeah, it's a good thing that you know what you're going after. What do we learn from this measurement? Like, are there some interesting physics that can come out of this measurement?
Sure. So that is the philosophical question kind of thing that we're talking about. Okay, so this is a clear probe of the thermal and ionization history of the universe, and these peaks come from pre-surface of last scattering. So there is something interesting there in itself. Again, we can go into if we see something else at a higher level, we don't know where they come from. If we don't see this, which is a sure shot kind of inevitable distortion from standard cosmology, that's interesting in itself. This is just a measurement. This is just a detection, but we push this and go from the detection domain to measurement domain. We can learn things like primordial helium at a fraction of primordial helium. We can learn independent measures of baryon density, the Hubble constant. So, but that's in the measurement domain, and right now we're like, let's just make a detection, which is like a statistical detection.
Thank you. Really good work.
Yeah.
Okay, I think it's not working. So really great talk on Pertush. I think I just see a number of strengths in the way you're approaching the entire design, and I'd very much like, if you're running a tour, I'll sign up. But one thing I did notice is the antenna, the antenna structure itself just looks fragile. The way that the antenna is coupled down through the what I'll call the ground plane.
Yes.
And you're agreeing. So yeah, can you comment on that?
Yeah. So I agree. Right now, we are in a domain where we think we have something that we think we can demonstrate in terms of its functionality on the ground. But in terms of making this something that is rugged and robust and maybe lightweight, we will want to work with the space agency to help us figure out how do we do this but better that can actually fly. But I do agree with you. Right now, the way we do this in the ground is we have this kind of thing that's like an inverted cone, like a point, that's balanced on a point. We support it using like foam, which is electromagnetically transparent, but we can get away with that on ground. We don't think we can get away with that in space, and we are working on that. We don't know how to ruggedize it yet, but we will. Yeah.
Yeah, I had a question.
Yeah.
Like on Earth, we are protected. The magnetic field protects us from charged particles like the solar wind and cosmic rays. Do you have that protection on Moon also, or on the far side of the Moon?
I don't quite know. I'm not sure. That's the answer. I do think that at least when we are specifically observing, we expect to be observing in the far side when we don't see like Sun or Earth. So during that phase, things might be more stable. But since this is orbiting, we will get hit by various things, and that's where expertise of taking this from a ground-based, especially electronics components, to something in space will come in.
No, because I was concerned because the Moon is moving in the solar wind.
Yes.
And there will be a turbulent eddy
Yes.
in the solar wind on the backside, on the
absolutely
right. There may be streamlines here, but on the other side there will be a turbulent eddy.
Yes.
I think the flow will be turbulent.
Yeah.
Which may be a concern.
Yes.
For
Yeah.
the
It
far
is,
side of
and
the
I
Moon.
think in some ways, for example, there have been some papers that we have seen that kind of measure how this changes antenna behavior, and to that extent, we're trying to understand that how that happens. But in terms of the details, I'm not sure. Yeah.
Thanks.
Hi, very nice talk.
Yeah.
On the recombination end, Rod, I have a question. So, how you decide the window? What are the main challenges in pushing towards slightly higher frequency?
Okay, so the philosophy we went with is you have a certain signal, and we want two things. We want to maximize signal to noise ratio, and by signal, I define signal as this baseline subtracted ripple, and everything else is noise, including atmosphere, foregrounds, synchrotron, everything, as well as your receiver noise. And so that is one aspect, which is what I've shown here. The signal does get stronger as you go to higher frequencies, like you might know. But we also want, if you go by the radio frequency technology available right now, we want to have, we want to design our experiment over 1 octave. So we don't want to do a multi-octave experiment due to just challenges that come in itself. So over 1 octave, we want to have at least 2 of these ripples, so we can distinguish them from foregrounds. So it's a combination of that, and that sets the upper limit as about something like 18 gigahertz. And just the kind of atmospheric window and receiver technology kind of gives this peak. But you go higher, you get the signal to be brighter and wider.
Yeah.
But once it gets wider, it becomes multi-octave.
Okay, because what will be interesting is that if we can choose another band slightly at a higher frequency, then reconstructing this signal will be easier also, relatively easier and more interesting as well.
Yeah. I understand. So I think right now we're like limited by the sampling technology
I
if
see.
you want to directly sample.
Yeah. Thank you.
One part in a million.
Yes.
So if there was, let's say, Y distortion as
Exactly,
well,
yeah.
that would not be the case. And
Yes.
current limits would certainly allow there to be something like about 100 nano-K signal,
Yes.
which
Yes.
has not been detected.
That's true.
So as Shobhadip just said, having two bands would
Help.
to pin it down.
Yeah.
Thanks a lot, Mayuri. Very exciting stuff. I was wondering if you could elaborate on the fact that you said you might be able to detect some of the signal from the Earth orbit itself, but it was not clear that this is function of amplitude, right? So you can, it seems there's a wide variety of things, which is both red and blue line.
Yes.
I would have expected like a stronger strength signal can be detected from Earth, and then Moon can take us to even weaker signal.
Right.
And other question I had is like, what kind of integration time you can go on Earth orbit without keep improving signal to noise, and how that will be different for Moon?
Sure. So that's a great point. Again, I should have emphasized here that here we have assumed a foreground separation technique that kind of gives us more sensitivity to signals based on how quickly they change. So it's not just a function of amplitude, but how rapidly the signal is changing, so how non-smooth the signal is. And hence you see like a variety in terms of the amplitudes, but you might notice that most of them have a quick turning points. And that is what this is a function of. And here I think I should point out we've assumed a somewhat worst case scenario for the lines in blue, where we have completely masked out everything above 85 megahertz or so, 88 megahertz or so, where we do have the FM band. So this is like if we see nothing other than FM, and as in we have no other RFI other than FM, and we have the entire 55 to about 88 megahertz, these are the signals we'll be sensitive to. But they need to change quickly in that band, in the 55 to 88 band. Sorry, other question.
About the how long you can integrate in on Earth orbit and Moon.
I think partly it will be a function of how long we are able to go in orbit in terms of the feasibility, technological feasibility. But right now we have assumed a 2-year mission lifetime, and actual science integration time we have assumed something like 2,400 hours, of which we might lose some data to flagging, etc. But that is the lifespan we've assumed both for our lunar as well as Earth-based experiments, Earth orbiter.
So, as I understand, so you need a dipole to detect the signal. So, why this conical structure? So, this is just to focus the signal, or?
Yeah, so we are not using a dipole. We are using a monopole.
Okay,
and
monopole.
yeah, so dipole again from some experience we have been building up using the various generations of Saras, we have moved away from dipoles because it's there are several challenges in terms of the balun, which is basically the thing that you connect the antenna to the receiver, and to make that smooth over the entire band is really hard. Secondly, you have always some kind of reflections that bounce around between the antenna, the dipole, and the ground. The ground has to be like finite, and all of that at this level, a part in a million, starts showing up. So we have kind of gone into the monopole approach. It's a simpler system, and you can directly connect your antenna pin to your receiver, and that's easier to understand and model and make that smooth. So hence, this is a monopole and not a dipole.
Okay. One more thing to what I was saying earlier. I mean, Govind Swarup had once mentioned that the moon is a radio source also because of the high energy neutrinos which fall on. I mean, that also, I mean, is a potential hazard. Right?
Yes, absolutely. So we the way our beam is, because it's so huge and it's a dipole, we will be seeing whatever is beneath it even in the far field. So if we're orbiting the Earth, we will be seeing half of the beam will be seeing the Earth, hence we will pick up the RFI. Similarly, if you're over the moon, you will be seeing the moon and things bouncing off of the moon. So that will all get picked up, and we have to understand that, and that will help us.
Okay, let's take the thanks Mayuri and take the discussion to the coffee. There is an announcement.
Our next speaker will be Abhirup Datta. He will be talking about peering into low frequency radio sky through seams.
Thanks to the organizers for giving me the opportunity to present this. Another one in the line. We have heard two talks in the morning about future of radio astronomy from space. This is going to be one more. So the experiment I'm talking about is SIMS. This is space electromagnetic and magnetic sensors, electric and magnetic sensors. And so typically you have seen this slide over and over again. So typically when I give a talk, there are three portions of this talk. I will be only talking about the part which connects to SIMS and more elaborate on the design of the experiment and what is the current status and so on and so forth. The team is here. It is a experiment which started from Pune University actually by Anand Krishnan and their colleagues in the Pune University Electronics Department. You notice after the first two, the all rest is students. And they are mostly graduate students, like master students, undergraduate students. They come and go. The list is long. From Indore, we are gathering three of the students are here, and few other colleagues who are discussing to join. Then people from ISRO, PRL, SAC, and RRI, now Ayuka, Avinash Deshpande. So long history. It started actually much before I joined it. I joined very recently in 2016 or so. It was 2005 when it was first called GEMS, and then it was proposed to the Chandrayaan-1 as EMS, got rejected. Then it proposed as LEAPS, keep funding going, then SIPS, then finally it becomes SIMS, which is the current status. So what is the current scenario? So there is an announcement of opportunity under which Pratyush was also shortlisted for seed funding. The SIMS was two, along with two others. And so we finished the first phase seed funding design study basically by sometime March 2022. Still some funding remains. So in between what the team did, there was another proposal for using the PS4. So those who do not know, there's a PSLV stage. PSLV is a rocket which is launched for most of the satellites by ISRO. And there's a stage 4 which kind of revolves around the Earth and comes down finally. And the life cycle can vary between few weeks to few months. So ISRO made it open call that you can use the PS4 as a stage, as a platform to design your own experiments and do it. So we proposed whatever the concept design prototype experiment, the instrument we come out for SIMS, that will be staged in PS4. That also got accepted. And so right now what we're doing, we are going from this design study mode to try to see how that prototype which is developed can be flown in this PS4. We learned a couple of things like the prototype of the electric antenna. We will show you that. RF front end has been designed well. FPGA data analysis and the other ancillary data product, how to communicate that back and forth, mostly back from the spacecraft to the ground station. All this has been done. Full pipeline has been activated, and we are doing some interesting experiences with the RFI, which is mostly self-generated, and we'll show you some of those results. Preliminary calibration of active antenna has been done. Noise floor measurements also has been done, and FPGA is now more or less concrete to be the final design. So why there's a need for SIMS? SIMS is going to operate below 20 megahertz, so down to 300 kilohertz or so, give or take. And so there was, so ionosphere becomes a very big problem, as you have already learned, below 100 megahertz, and definitely cuts off at sometimes somewhere around 10 megahertz or so, depending on where you are on the Earth. Okay. So sometimes you're not that lucky and things cut off around 20 to 30 megahertz or so, even higher. So, and then we are seeing a lot of results from the low-band, low-far antenna, low-far experiments and LWA that pushes the boundary now closer to 20 megahertz, around 50 megahertz or so, but still not many experiments which are operating from the ground which crosses this barrier, which is obvious. The previous, but there are a lot of mission designs. You have heard Jack's talk in the morning. I was involved in the group in the beginning. So there are a lot of concept missions which has come up, which is good. The literature is very, very rich. and a lot of different things. All far came out, Darius, Pseudo, Dex, even Leon is attached to a couple of them. And then one of these missions which finally landed up in CLE, everybody was eager to get some results, but nothing, it's completely radio quiet from that side. Result front, I mean, something has happened. The previous known results from RE 1 and 2 were very poor spatial resolution. So, and they were not to be, cannot be used for going further in doing any cosmic observations. Another reason why something like this for PS4 also should be done is there is no RFI measurement in situ on the LEO or above. So how much is actually, what is the RFI situation around, what should be your specific design of your instrument that has to be done. So the way we propose is the phase 1, which is this stage 4, which is now approved, and it will be done very soon. Some funding issues are there, so that is mostly because of the based on the COTS components will be done. So, but there are issues which I will keep on doing, but still, nevertheless, this is an exciting opportunity to fly your prototype instrument in the space. Phase 2, of course, the next phase will be, going to the far side in the orbit, and there your main science science goals are detecting CMEs, planetary auroral kilometric radiations, then several magnetic reconnection events, and finally H1 cosmology. And the portion which we will be interested or sensitive to is like complementary to Pratyush is in the dark ages. So we have already spoken about this. So I think we have proceeded this particular phase of study, which is currently going on, is delivering the payload for the PS4 deployment and moving forward to discussing with ISRO and how to take things forward from then. As we say, the science goal for the main mission is, first of all, studying low frequency sky at below 20 megahertz. This is not done and cannot be done from the ground. Very rarely, if you see in the solar minima, things become a little bit more transparent, and you can still see, radiation coming from these frequencies. And but again, the systematics are probably pretty high, so you still need to observe it at a lower frequency from the space. Study solar wind, and at this particular frequency, there is a lot of space weather boom now. So that's one of the another science goal. And of course, galactic and extragalactic radio spectra at this frequency. So this design is basically driven by a tripole antenna design, so it won't be doing interferometry or so at the beginning, at least. This is the how the flux density of different contributions look like. This is a solar burst. This is galactic background at this frequency. This is Jupiter's AKR at this frequency, going from 100 megahertz down to 10 kilohertz. And then finally, the reason I'm interested in this is because of this cosmic dark ages. So you can see this slide from the DAPR team that you have this dark ages signal going below, near about 20 megahertz and below. So you can do pure observation from this. It's not trivial, but if you go forward in this mechanism, it can be proposed to be done. So why lunar far side? As you can see this slide that now thrice today in the morning. That is the spectra taken by RA2, and you can see all these bumps and wiggles are when the orbiter was facing towards the Earth, direct line of sight, and this low region is when it was completely shadowed by the moon. So moon acts as a good shielding at these frequencies, but it doesn't actually consider the entire limb to limb to be as a shield. Because of diffraction. This region kind of reduces, which is a work done by Neil Bassett and Jack Burns' group. The other thing to go to moon is basically ionosphere, and we have done this study a long time back. And if you go further and further below, what actually happens is it's like similar to the pink noise or 1/f flicker noise in your electronic systems. If you don't calibrate for the ionosphere, then that builds up and no longer you end up with having a mean, which is meaningful. So mean also, gets changes as a function of time. So calibrating for the ionosphere is essential, and sometimes you don't are not able to do that. So that's why you have to go to the space. One of the major reasons why. This is how the SIMS payload looks like. This is the outer side, the antennas, and this is coming in. This is the analog front end. This is the FPGA back end, and then finally the power supply and so on. So we will show you the actual thing. This is just a cartoon chart to show you the exact design. So much of this work actually done and now frozen, and we are up to the specs to deliver that. So this is this is a PS4 kind of a cartoon, how it will look like, and this is where the two dipole antennas look out. Now, one major difference between PS4 stage and the phase 2 will be, in phase 2 we are designing it as a tripole antenna, but in PS4 that is not possible to be flown because of the how you deploy on the PS4. So we are sticking to simple dipole antenna. Okay, and that also we have a problem because we were actually, if you are looking at these frequencies, you need a 7-meter kind of a length of the dipole, but there's a limitation of what ISRO has done so far and what they are comfortable with. So we are sticking to 3-meter for now because of the suggestion received from the VSSC. Several different materials have been tried. This is known to many of you. This is what it looks like if you do it in the CAD drawing where it sticks out of the PS4 stage. So first we'll start with this kind of a self-deployment mode. We tried this one. This motorized deployment also have been tried. And then finally a lot of things have been tried to be done. And finally we found out, and I think zeroed in on something called stator antenna, which also you have seen in the paper talk in the morning, and I will show you a video how it is done. Actually, we accidentally got into this. There is a magician in Kolkata who uses this as a magic wand, and from there, one of the students actually found it out. It's a nice anecdote, He was looking for, his job was to look for alternative to this motorized deployment, and he was looking into thing and found a magician who uses this kind of thing to stun you in the tricks. And actually the first prototype was actually acquired from him. And later on we found it on web. So this is the short video. Oops. How this guy deploys. Okay, so still there's quite a bit of kickback, and that's one of the challenges what to do. So this is where the thing sits. These are two orthogonal stator antennas, and you basically have this Teflon thread over here, which needs to be cut. And once it is done, then it is deployed in the two sides simultaneously. So what is the amount of reverse thing that has to be calculated and make sure that this does not get shoot out of this thing altogether. That's what have been done so far. So there are a lot of advantages and disadvantages for this particular one, but we thought finally the team came up with the thing that this is probably the best possible case we can do at this particular stage. So we go with that. Another thing, if you go back to the antenna, basic antenna textbooks, this is a very well-known thing. As you're going lower and lower in frequency, no matter how sensitive antenna you make, you have to make a matching network. Balanced to unbalanced, balanced, we have studied all, but it's not very well appreciated unless and until you actually come and do this. You may build a larger antenna, but you don't detect anything. Then you say, what the hell is happening? So the entire trick is this, making a accurate active matching and network. Okay, so that was lessons learned and known, but then how accurately we do it is the lessons learned for this process. This is the glimpse of the RF front end. So this is the box all fabricated. There are third party in Pune who does it. This is the FPGA backend thing, 2 channels ADC, and then finally, nothing, immediately novel here, but the size has to be compressed into a thing. That is the main thing. And what we learn, I will show you. I will not tell you right now. Self-shielding all these things is very important, and we will see the results of that also. This is how it looks like, the FPGA backend board. It's based on the Vertex 5. We also did all those calculation of our data storage, what is the data rate of bringing it down to the ground station. There is a strict requirement of keeping it low and all this, particularly for the PS4. All those have been calculated and done. We have using Raspberry Pi 4 as for monitoring the system and sending answer data back. All these are done. Yeah, this is how it looks like. 15 by 15 by 15, this is the payload, what it looks like. They have these 3 distinct stages. The top one is where the antenna deployment is there and the matching network for both the antennas. Then the front-end gain stages, then the final digital backend, and this Raspberry Pi 4 and EPC stage. That's what it looks like if it is assembled. But as you see that there is no room for the third one. So when we deploy the final one, the tripole, we have to do something more novel than this. So very good, this is done. But now we deployed this in the top of the building in the university with a flat ground screen. We see a lot of this stuff coming in. This can be thought of as a transmission and RFI, but what is this was not very well known at that time. Kept on observing nights over nights. So you got the waterfall plot. All these are fine. Then finally we understood, okay, we thought that, okay, maybe we are not doing the right job because PS4 will be a curved body. So the ground screen is basically curved. So we should mimic that by, putting in a tent and putting chicken wire on top of it. And then we took the result thing. And this is what I think the hump is because of the ground plane structure. So now it is actually known that what might create this thing. So previous one probably was because of this finite ground screen length. We are not going far enough, which is already well known. But what are these? So because it is in Pune and NCR is nearby, so the Yashwant, gave the permission to use their radio Faraday cage and do this simple observation. So we did 2 things. First is the digital backend being shielded and not unshielded. These 2 were done. So this is where it is not shielded. You see all these bumps and spikes coming in, but when it is shielded, they're all gone. Okay. So that basically means the shielding internal component, probably already known, but still, every time you make a new instrument, you have to discover all of these things all over again. That's what is, but very helpful that we know now. There are several outcomes of learning from here. So design consideration for digital backend were also there. I mean, there are 2 channels are required, so we stick to this Xilinx ultra scale XQRK use 60 board, and what we yeah. So from the space point of view, as I said, that this is good for PS4 because we are only having the dipole, but when it finally goes into the lunar orbit, we still need to figure out that this is not enough space because the third antenna will sit where. So it has to be at least one more. So 15 by 15 by 15 is not a sufficient space. And this is already overboard than the standard 10 centimeter by 10 centimeter, 10 centimeter, which is kind of 1U typically. So that's the challenge which currently we are addressing, that because there is probably an interlude between our phase 1 and phase 2, that something can be done probably from the LEO, but then only the things which can be flown are only based on that 1U, 2U, 3U systems. Okay, so this is the projected milestones from phase 1 transferring to phase 2. We've already started doing some work based on that, like the design study for that 15 centimeter cube box, how will it accommodate the third antenna, and so on and so forth, that already undergoing. And how to make it more compact by slicing something and fitting into this 1U, 2U, or 3U unit, kind of, because you have to at least keep the other 2 dimensions 10 centimeter each, and you can stack up basically in the third dimension. You can go to 30 centimeter also. That's the work currently going on. in the team, and while we wait for a little bit more of clarity on when to fly, and a little bit more hurdle budget-wise is there to go that extra step. So the phase 1 deliverables are mostly done. We are confident what things have been working. So that is good to fly, barring a few more details, which is digression right now. But yeah, as we gear for the phase 2, there is no natural progression from phase 1 to phase 2 in ISRO's case. So we are all in the same boat, Pratyush, us, and 2 other experiments. So I think that is where we have to, we are creating noise and we are presenting and trying to see how it gets a natural progression from design phase to the next project mode. Few suggestions also received. But before that, just last bit of thing is that how will we localize the sources? We have a triaxial electric field sensor. How will we localize the sources? So we adopt this standard method of direction arrival by using goniopolimetric technique. So one of my students, Harsha Tati, he has been working on this, and he adopted the standard matrix pencil method of doing this thing, and doing this thing, and he basically used it for several snapshot averaging mode and modified this thing, which actually works better for a spin stabilized system, and that result has been submitted to Experimental Astronomy as a paper, and we got the first review as a favorable one. So if the reviewer is over here, please, we have submitted the revision version, okay. So yeah, so this is, we can talk about more. So this is the progression, natural progression chart going from phase 1, which is a PS4, into the next stages. We added an interlude in between, that is as having a CubeSat or a small sat, after discussion with several ISRO people, and that this may be possible, and then maybe shaking hands between the 2 extreme ends of the spectrum experiment for EOR and Cosmic Dawn and Dark Ages may be possible. That's also we are discussing with Pratyush team. We thank you. We left you with this. It's nothing to do with SIMS actually. This is one of my students who's developer, is among the thing, Rashmi Sagar. We have a band 2, 150 megahertz image from GMRT. Looks absolutely spanning. So I just thought of putting it there. Thank you for your attention.
So we can take some questions.
It's very, very nice to see the progression. I was also the receivers that sort of spring out, so they look very helical. So I don't know if that has an influence on how the voltages progress along the receiver, right? Does it have an effect? Because I would think that the voltages might go in a helical way as well, and that will actually impact your sort of directional sensitivity.
Which one?
So these sort of magic wand receivers.
No, it doesn't. But there is some other issues, like there's something for cold welding. I mean, they kind of stick together, and there are ways to do it. You have to use different materials to avoid using that. But typically, they have been. I mean, it's not that well known in ISRO context, but NASA is very, very familiar with flying this kind of things. That's what even Jack showed in his Lucy slide, I think.
But they act like a normal receiver that's solid. Even though it's helical, the current still travels in a straight line.
Still travels in straight line, yeah.
Okay.
Yeah.
Thanks.
But based on the joints, how?
Yeah, that I was thinking. Yeah, it needs to be really joint, otherwise you get very strange behavior.
Right.
Thanks, Abhirup. This was really nice to see. So what are you doing to get away with the self-generated RFI?
Yeah, so they are now shielded. I mean, they have used a separate, they have changed the way it was fabricated earlier. And so we are moving on to a new board, which have this shielding in place, so this can be done. Previously it was done by hand, now it is actually in the design. Yeah.
Just one related question is this FPGA board that you showed, it's nice to see how small it is. Is the clock source inside the board, or you get the clock from outside for your electronics?
I think it's outside.
I see, okay.
But I have to check.
Okay. We can talk later.
Yeah, sure.
Thanks, Abhirup. Very interesting stuff. I was wondering if you could, maybe I didn't understand this. In the phase 1, when you're going in low Earth orbit, the lifetime will be of order weeks, did you say? And so will you?
So phase 1 is in PS4, PSLV stage 4, and the lifetime can be enhanced up to few weeks to few months.
I see. So in that case, will you be
depending on when you get a chance to fly, and it's those kind of things. Yeah.
Right, and so this will be to measure the conditions on Earth.
Mostly
itself,
RFI,
right?
mostly RFI scenario in the Leo.
Okay.
And if lucky, then get some sense of a spectrum of the sky as well.
I see, and the fact that this is very dynamic, for example, day-night variations, will you be able to measure those sort of things?
Yeah,
will you
so
be able to have multiple orbit in different conditions?
That depends on a lot of moving pieces. We need to know exactly how the PS4 stage is tumbling, around which axis, and those things. You have to understand, this is not how to say, this is not a tracked part of the entire body. It is just has to be thrown and nicely shelved off to some part of this ocean or something, right? So we can only ask that much from ISRO to how to monitor, how much to monitor. So we need all information, every possible, like which way it is spinning, how it is rotating, and all these things. So depending on how much information we can get, that depends on success. So that's why Leo, in putting something in Leo dedicatedly and on a CubeSat or microsat is important. That's what we were saying. But anyway, we got that, so we can fly that anyway. All right.
So if there are no more questions, we can again thank the speaker. So our next speaker is Joseph Lazio, After the Sunrise.
Okay, it's great to be back. I was actually here about 5 years ago having discussions. At the time, there was interest in either JPL or NASA collaborating with ISRO. And the idea of a space-based low radio frequency telescope was one of the topics, or I came over to explore, could we do a space-based low radio frequency telescope? And so Raman Research Institute was among the places I visited, and what you're about to hear, I don't think it really resembles anything that we discussed at the time, but that trip to India, I think, is one of the foundational points for the Sunrise mission. So, thanks to the organizers for the opportunity to come back and tell you about it. Okay, you've already heard about all this, right? Great cosmology based on the most simple atom. I want to emphasize the power of 21 centimeter cosmology. So it's rare that you see papers that talk about ultimate limits. But if we can really do 21 centimeter cosmology in the dark ages, that's the end of cosmology. There's nothing more you can get out of our universe because you sample as many modes as there are. So it's a fascinating possibility. I think, as we heard earlier, it may be a bit challenging in terms of 100 square kilometers and things like that. But there's a real potential here. And of course, we've already had a dry run with edges, right? There's incredible theoretical interest in explaining what edges saw. Regardless of whether it was an actual detection or not, that still, I think, illustrated the possibility of new physics and pushing beyond the standard model. Okay, so that's all the stuff that, I'm actually not going to talk about this anymore. So at some level, what I'm about to describe has nothing to do with this cosmology, and yet it has everything to do with it. If you go back, this is actually a neat conference proceedings from 1990, if you can get your hands on it. Conference proceedings by Namir Kassem and Kurt Weiler. One of the long-standing reasons to do space-based low radio frequency has been solar radio physics. And in fact, much of the foundation has been laid in India in terms of looking at metric type 2 burst and the like, of studying the sun at sort of meter wavelengths. And even today, decades after some of these phenomena were understood, we don't understand very basic physics. So this plot here is a dynamic spectrum, time on this axis, frequency on this axis, with the power illustrated logarithmically. And two things are notable. There are these type 2 bursts that drift slowly downward in frequency, and type 3 bursts. Again, those have been known for decades. They haven't been as well studied from space, but they have been well studied from the ground. These are pretty clearly associated with coronal mass ejections, and there's a lot of talk in the literature about coronal mass ejections produce shocks, accelerate particles. That's a Pavlovian response, right? Shocks must accelerate particles. That leads to the type 2 burst. And then the type 3 bursts are clearly somehow associated with jets of accelerated electrons, electron beams moving out along magnetic field lines. Let me talk about type 2 bursts because they really drive a lot of the aspects of the Sunrise mission. And from an astrophysics standpoint, the sun is somewhat a laboratory for particle acceleration, you know, sort of right there in our backyard, so to speak. And there's a lot of commonality between the shock acceleration that might be happening at the sun and what we see at supernovae and in clusters of galaxies and things like this. So here's your standard coronal mass. Well, here's, you know, perhaps a beautiful picture of a coronal mass ejection. It's taken through a coronagraph. So by way of for reference, this white disk here is supposed to represent, it is the sun. So this part, the sun has been blocked out so you can see the corona. And one of the big open questions is the coronal mass ejections clearly accelerate particles. One of the things that's been realized in the sort of the past decade is whenever the most energetic particles are detected, it's always preceded by one of these type 2 bursts that starts at about 15 megahertz or so, a so-called decametric, hecametric type 2 burst. So every time we see accelerated particles, or one of the spacecraft, you know, one of the flying spacecraft are hit by particles, there's been a type 2 burst that precedes it. Not all type 2 bursts, however, are associated with these accelerated particles. So what's happening, and one possibility is simply that the accelerated particles can't get from the coronal mass ejection to the spacecraft. And I think I'll show you an example of that. But there are very basic questions about where are the particles being accelerated and what are the mechanisms. So one possibility, there's sort of 4 classes of models in the literature. One is the acceleration is happening at the shock front. That's kind of pretty obvious, right? You've got a shock front moving into an ambient medium where there's magnetic fields and it's accelerating. Another possibility is that it's happening at the sides here, and as those move laterally into the solar wind, then they're accelerating particles. And in fact, there's some limited evidence from LOFAR that might be happening at higher frequencies. But in both cases, there could be aspects of diffusive shock acceleration, which is, again, you think about supernova remnants or clusters of galaxy, diffusive shock acceleration is the way to go. Maybe it's magnetic reconnection behind the CME. And then there's some intriguing models, sort of a non-local acceleration. You've got this massive CME plowing its way into the solar wind, and it just stirs up enough material elsewhere in the solar wind that you get accelerated particles. So what we'd really like to do is, and the argument for the Sunrise mission is, if we have angular resolution, we can take a radio picture of this, because right now this is a white light picture, right? This is what our eyes see. But if we took a radio picture of this, with enough angular resolution, we'd be able to tell you where the accelerated electrons are. And if I can tell you where the accelerated electrons are, then I can tell you where the protons are being accelerated, and we can rule out possibly three of these 4 models. So that's the idea. Whoops. Okay. Oh, and in fact, here's the idea. So if we could tell you that, for instance, the particles were being accelerated, or the radio emission was occurring, say at the nose of the CME versus the flanks, then you could trace where the magnetic field lines are, and do they actually connect to a spacecraft with a particle detector, and possibly, you know, again, rule out those models. But in order to do that, you actually need to be able to take radio pictures, so to speak, of the CMEs, and we don't have that capability yet. So here's, again, I'm sort of hammering home this point. This is the idea. We'd really like to put the radio X on the coronal mass ejection and say, that's where the particles are being accelerated, because that's where I see the radio emission. But these dynamic spectra are the state of the art. They've been all we've got for the past 50 years. And there's essentially no angular resolution, or the angular resolution is like a radian, right? Well, the radio emission is coming from that direction and not from that direction. In fact, again, LOFAR's done some of this. Actually, Garabedinar has done some of this. So here's an 80 megahertz image illustrating the idea. There's a CME that's starting off. There's the 80 megahertz emission. And the only problem here is it seems that the real interesting particle acceleration is happening when the CME is at about 5 solar radii. In this case, that CME is about 2. And the radio emission is coming out at 80 megahertz, so you can see it from the ground. And by the time the CME expands out to about 5 solar radii, the frequency has dropped to something like 10 megahertz. You can't see that from the ground. Okay, so there's what we'd like to do. What we're going to do is we're going to build an interferometer in space, so we get the angular resolution, and that's the concept on the right. We now know how to. Now think we know how to do this, or the technology is there to do it, and it's combining two very well-developed technologies. We've been doing space-based decametric, hecametric measurements for decades now, and we know how to do aperture synthesis interferometry. So if we can just combine these two, we've got it. Okay, so to date, this has all been PowerPoint slides, and there's the PowerPoint telescope. Now I want to show you some real hardware that's being built, has been built. So here's what we call the science payload. This is the actual part that's doing all of the hard work of measuring the signals. So this is the top view. We have, and I'll show you in a moment, but these are the 4 stasers. So you've heard reference multiple times. They're probably about yay big or a little larger than a, sort of a finger, and a little bit larger round. So these things are relatively small. All of the electronics sits underneath here. And I'm going to come back to this picture because this picture is actually, it shows one of the key experiences has been gained. Here, you do the testing of it, payload testing. Here's the actual staser deployment, one of the tests that was done. So it's going over here, and you'll see it go, boom, there you go. So it goes very fast. Do not stand in front of it. And also, once deployed, one of the most serious injuries ever received from these things is somebody actually took hold of it, and it's a coiled spring, and it's really sharp. And so there's apparently blood all over the place. Okay, so, and there are multiple, right? One of the key aspects, and I think, we've kind of figured out how to do this on the ground. GMRT has 30 antennas. We know how to build tens of antennas. SKA is going for thousands. This is not standard for the space industry. Certainly it's not standard for NASA. NASA likes to do one big spacecraft, it's something unique, and then it goes on and does the next big spacecraft. One, right? Here we're doing actually 6. And suddenly you've got to start thinking about, how do I do assembly lines? How do I process multiple things? Where can I keep the schedule efficient by doing things in parallel as opposed to testing each thing in serial? Here's the spacecraft. So this is a 6U spacecraft, 10 centimeters by 20 by 30. You can. I'm not going to walk you through all of the aspects of it, but you can see it's really jammed. Another important thing to note is, so actually 2 things. The science payload fits in right here. So most of this volume is actually not the science, right? Most of the volume is associated just with keeping the spacecraft healthy and getting the data to the ground and things like that. This actually, as part of an EMI effort, this actually forms a Faraday cage. So the science payload is stuck in here with the rest of this, with the intent of shielding that all. And that's the artist's impression of what it would look like in flight. The solar panels, actually, the way it will be oriented, the solar panels will always be facing toward the sun. So the dipoles on the back are actually, they're on the back of the spacecraft. Here it is. Here's an example. So this is Tim Nielsen. We are actually we at JPL are buying the spacecraft from Space Dynamics Laboratory in Logan, Utah. So Tim Nielsen is the project manager there at SDL. You can see this was a briefing, and you can see various components of this spacecraft, again, lined up. How do you do an assembly line production? You can also see, I think, sort of what, right there is one of these. This was one of the engineering model stasers. So the dipoles, when deployed, are 5 meters tip to tip, just to give you a sense of what the scale is here. And interestingly, you can see this is gold, or whoops, it's a gold color. In flight, and this is completely non-intuitive, in flight the real ones are black, and that actually is a thermal issue. That by making them black, somehow the thermal, it's more thermally stable than if they were gold, which is still, I don't quite get it, because then you look at all these other spacecraft and they've got gold blankets on them and or gold-colored blankets. Oh, and another important thing is, okay, yeah, you can build the science payload. Can you actually process the data? So I haven't gone much into it, but it's kind of standard interferometry. It's actually, let's see, I'll just say that the science payload itself, it's an FX correlator. So the science payload does the Fourier transform part in flight, and then the data are beamed to the ground, and the actual correlation happens on the ground. So that's another aspect of, we intentionally try to keep the spacecraft stupid and do the really important stuff on the ground. And this was one of the movies that the guy who originally made our science pipeline put together. Here are the four different models for where the particle acceleration, where the radio emission might be happening, trying to make the argument that we could actually process the data and distinguish between the different models. And so these are actually, importantly, right, I said originally we'd be taking pictures. Actually, these things evolve in frequency, so the intent is that we'll be making movies. And the argument is we think we can actually localize where the radio emission is as a function of time and track where the particles are being accelerated. And in fact, what's happening right now, and one of the reasons I wasn't here earlier in the week, is what we are calling the interferometer level performance test. So this is part of the setup, and I couldn't get the picture in time to get it included, but we now have 4 spacecraft on one bench and 2 spacecraft on another bench. They've been all wired up, and they're working. It's as close to being 6 spacecraft in flight and tested as you can get without actually flying them. We think this is the first time that's ever happened. So we're actually trying to feed them Mach signals, downlink the data through the space radio at that bit rate, and I'll come back to that, but at that data rate, transfer that over to the JPL's Mission Operations Center and then on to the Science Operations Center and do the correlation. So as if they were really flying. And so this is ongoing right now. So far, actually, we're seeing some anomalies. A lot of it is stuff like, oh yeah, somebody said these files are supposed to go in this directory and that message didn't get communicated to somebody else. Or, oh, you mean the transmitter turns off when we thought it didn't, and things that it's a good reason to do the test on the ground before they're flying. The orbitology. So people often ask me, are we doing formation flying? No, we're not doing formation flying. So the mission design folks came up with really neat orbits. So just for reference, the blue disk is supposed to represent the Earth. The yellow disk is the sun. I haven't said it. The spacecraft are actually they're actually slightly above geo. So think something, or will be. So think something like a 25-hour orbit. And so that, you can sort of think of that as the guiding center or reference orbit for the constellation. And in a second here, it's going to zoom in. This was actually, we actually had a hologram sort of, or an augmented reality, you could actually watch this. So this is an attempt to show you in 2D what's actually happening in 3D. Here are the spacecraft, the orbits, so all of them are on sort of circular orbits, but they're designed to stay within a 10-kilometer sphere. So we need a 10-kilometer sphere to meet our angular resolution requirement. And you can see it's this really complicated, and then you get the vertigo thing because we're trying to shift and show different perspectives. And a second here, okay, so this is now a sort of actually formally like a 6.5 kilometer diameter radius. And the idea is, well, you build up the interferometer from the unique pairs, and each unique pair gives you a sampling of the UV plane. I think in the interest of time, I'll keep going. Okay, so this is kind of where things stand at the moment. We are in the midst of actually sort of what's in NASA speak phase CD, so actually building things and putting them together and testing and showing that everything's going to work. Actually, in a couple of months, those 6 space vehicles, as we call them, are going to be packaged up and then put on a shelf. We have a launch. We don't quite know what the day is, but the launch will be most likely in 2020. Well, it'll be in 2024. But the original contract with NASA was you have to be ready to go in August of this year. So to be ready to go in August of this year, that actually means the space vehicles have to be packaged up by sort of May. And that's, they're going to get packaged up in May, and then they may very well sit on a shelf for a year while we wait for the ride. So I think this is most everything that I've told you. 6 space vehicles in orbit. They're going to synthesize a radio aperture that's something, roughly 10 kilometers in size. They're going to look at coronal mass ejections. The data come to the ground. Actually, I haven't talked about through the Deep Space Network, funneled to JPL where the Mission Operations Center is, and then on to the University of Michigan for science operations. Oh, and then actually, all of the data are going to become public, and they're going to go to NASA Space Physics Data Facility. So, in 2 years or something, if you want to take a look at these data, they'll be available. Okay, so one of the ideas behind Sunrise was it was all supposed to be a pathfinder for something bigger. Something like, say 21 centimeter cosmology or other radio astrophysics, which was actually the topic of the discussions here about 5 years ago. So what are the lessons learned or experiences gained, if you will? One thing was the science payload. Okay, I would never do it this way again. Don't do CubeSats. I was astounded where we run these wires actually makes a difference in our sensitivity. So we're looking at 30-meter wavelengths, and yet millimeter differences in where those wires run affects the overall payload sensitivity. In retrospect, this is already known in the literature. Stuart Bale has some stuff on, I think it was the experiment he's flying on Parker Solar Probe. So my thinking right now, my recommendation is CubeSats may be a great place for testing out technology, but if we really want to do something like this, and maybe more generally, to do space-based radio astronomy at these frequencies, we're going to need larger things. And so one of my comments about Pertush was I think one of the nice things is it doesn't look like it's all being trying to cram together, right? It was like a 2 by 12 U or something. I think that is a wise, in part, based on this experience. And we already heard, I think, was it Leon asked about this? How do you determine where the antenna positions are? So I haven't really gone into this in much detail. For Sunrise, we are actually using the GPS constellation. So I haven't told you, but the science payload not only measures the solar radio emissions, simultaneously it's measuring GPS signals, and it's using those GPS signals to time tag the radio data, the solar radio data, as well as determine it post-processing, all post-processing. We're going to determine where the spacecraft locations are to something like 10 centimeters. So this is actually not trivial because most GPS is designed to be, you're supposed to be under the constellation, right? When you're picking up GPS on the ground or in low Earth orbit, you're under the constellation. We're actually looking at the side lobes and the GPS satellites that are on the other side of the Earth and that nonetheless happen to illuminate our constellation. So that works for something in GEO. It wouldn't work for something, say, in lunar orbit. I think you heard Jack say there are possible plans for sort of a lunar equivalent to GPS. I don't think we know what the requirements on that are going to be yet or what its performance is going to be, and I'm a bit worried that getting that in place will lead to RFI that vitiates the entire reason for going to the moon. This certainly would not work. I think the other good location we should be thinking about is the Sun-Earth L2 point. That's where JWST is, that's where Gaia is, that's where Roman Space Telescope. There's a lot of reasons for going out there. We don't have GPS out there. So how we actually determine the spacecraft positions with enough accuracy, even at 30-meter wavelengths, I think is yet, it's going to be a problem we're going to have to revisit. Data transport. So I'm a radio astronomer, right? I can do this. 10 megahertz, we're down at like 10 megahertz. So you can do a very simple 10 megahertz, 20 megasamples per second at Nyquist. We got 2 polarizations, 2-bit sampling. It's 80 megahertz. I guess I dropped it off here. But I did a speed check on my home wireless router a couple weeks ago, and it was running at 89 megabits per second. You go out to GMRT, and it's got, I think, gigabit per second or something close to that fiber optic links. Right? That's easy. The telecom engineer, when I first told her this, she fell off her chair laughing at me. We got 2 megabits per second. She said, you're going to get 2 megabits per second, and she was right. And that is not a technical limitation. That's a spectral regulation. So we are limited into how much data we can bring down, at least when we were building the Sunrise mission. Now, maybe in 10 years, there'll be better radios, and maybe laser comm that would get around some of this. But at the moment, this we can kind of get by with this. It amounts to bringing down about a megahertz of the total 20 megahertz that we're sampling. And we can live with that from a solar radio physics perspective because the sun is bright. You have to think carefully. Can you do 21 centimeter cosmology on a megahertz bandwidth? That's not the way we've all been thinking about it. And so actually doing that, I suppose this is actually another movie that I should have been playing. The other thing we're also doing to get around, not to get around this, but to try to compensate for this factor is we're actually, one of the reasons for using the Deep Space Network is we can bring down data from 3 spacecraft simultaneously. So that, yes, we're only getting 2 megabits per second per spacecraft, but we can actually get down 3 simultaneously, and that helps us in terms of just overall, that's actually an overall observing efficiency. So we have to take less time out of doing the science observations to downlink the data. The other thing is the mission architecture. So Sunrise is very much a classic VLBI telescope in the sense of you have 6 independent antennas. They don't know anything about each other. In fact, we argued that's a strength. They're completely independent. They do not talk to each other. This is Helioswarm, which is now an approved NASA mission. They have 9 spacecraft talking to a mothership. In fact, that was the original design for Sunrise. And the original system engineer, Farah Alibay, sort of looked at me and she said, "You are not doing that." And she was right, because that second mothership spacecraft would have driven our cost to the point we couldn't have flown the mission. But looking forward for 21 centimeter cosmology, and in fact, all of the times that I've worked on lunar radio astronomy, we've had a similar architecture of a lot of little antennas out in the field feeding a central hub, which then relays to a relay spacecraft. So whether that's on the lunar surface or in lunar orbit or at Sun-Earth L2, that's probably the architecture we're going to need to do 21 centimeter cosmology in any real sense. Okay, that's my last slide. Everything I've already told you. Sort of late 2024, we think we're going to start getting first science data. The mission is a year long, so 2025 will be an exciting year. I hope it's exciting in a good sense. And then, but you can tell I'm already thinking after the sunrise. So thank you very much.
We will take some questions now.
Thanks. So I just had, thanks for the very nice summary. Off the top of my head, the 2 megahertz which you were talking about, the 2 Mbps which you were talking, you were asking if we can do this cosmology part on a 1 megahertz band. At least for intensity mapping kind of thing, like if you're not going to go too high resolution, I think it should be okay, because off the top of my head, the MWA 350 megahertz band, you can do good science with even a 10 megahertz bandwidth. The numbers are 6, 8, 12 and 3 channels, which I remember. So now if you scale everything to the dark ages kind of central frequencies, you're still going down a factor 5. And so maybe if 6 becomes 6 by 5, which is 1, we still should be fine.
Okay.
So at least I can see that this science case is not going to, it will still hold up. Yeah.
So I think the question is, the orbital motions, they're not, you asked about active. It's really, I think the way I think about it, I don't think this is quite right, but I think it's kind of like an epicycle. So they're all on circular orbits, but they oscillate just slightly sort of around this reference orbit. And then they're designed always, and then when you project them to 2D, so you're really supposed to see it in 3D. But yeah, they end up doing some kind of pattern around the reference orbit as it goes around. But the thing I want to stress is there's absolutely no, people often think, oh, you're doing formation flying, right? You're joysticking. Nope, they're on these orbits. I didn't say we talk to them once a week. So we talk to them once a week. We do this GPS post-processing. And if the mission design folks, if they decide that they are too far from the intended orbit, that will get nudged back on. But that's it.
So if you're limited in your data rate, have you considered some sort of smart data compressions? I mean, for example, with LOFAR data, we developed a compression right, by a factor 5, 6, without any loss down to the EOR level, so extremely high dynamic range. And it works extremely well on noisy data. Actually, it works better if you have more noise. So, I mean, have you thought about it, or are you just sending down the raw voltages sampled, or are you sending down the correlated?
We're sending down. We're doing a polyphase filter bank, but essentially a Fourier transform, and then selecting out certain frequencies to come down.
Okay.
And then those are somewhat downsampled in a bit sense, but there's not data compression in the way it's used typically in the aerospace industry, because there is an aspect of that can be lossy.
Yeah, so but we developed techniques where that loss is basically absolutely negligible, and you can gain a factor of 5, 6 in data rate.
It's too late to change things, but yeah, it'd be interesting to hear more details about, because that might be a way to get beyond the 1 megahertz or that kind of limitation.
Thanks.
Yeah, you're doing typically what is done in VLBI, like you're doing the raw dump and you're correlating in the ground.
Yep.
Right. So how do they get the same time stamping?
That's the GPS.
That's the GPS.
The GPS, there's an oscillator on board that's essentially slaved to GPS, and that's putting the timestamp on the solar radio data.
So they have to be in line of sight to one of the GPS satellite every time, which is probably is.
They can flywheel for about an hour. So if they're not in lock with a GPS satellite for less than an hour, the solution carries through that time.
Okay.
If it's more than an hour or hour-ish, then things will go off, and the data will be bad until it requires lock.
So, Joe, can I add on to Abhirup's question? So, the time tagging, do you do phase locking on the GPS carrier phase or on the code? What sort of accuracy do you need for maintaining your clock?
I think the question is carrier. Are we doing the carrier? Yeah, it's locking on the carrier.
Okay.
Yeah.
All right, great. And I had another question. How much time does it take for you to fill out the aperture, fill out the UV plane to a degree which you need to image? Is it on a few hour time scale or?
No, because the emission, I guess these are a bit small. Here. The emission evolves in frequency. So at any given frequency, a type 3 or a type 2 burst is actually at that frequency for only a short period of time. I mean, certainly in this case, it's less than a minute. So we're actually doing snapshot imaging, a modest amount of multi-frequency synthesis of trying to get a couple frequencies that are close enough together. But it's essentially all snapshot imaging, and we're saved in part because the solar signals are stronger than the galactic noise background. So we're in this very weird regime. I think that again to which we're not accustomed from ground-based radios, most of us, we're in a signal-noise ratio greater than 1 from the start.
We can thank the speaker again. So we now have lightning talks, 5 lightning talks of 5 minutes each. So our first speaker is Asif Ilahi.
So I will present this work which I have done with Professor Somnath Bharadwaj at IIT Kharagpur and with others, Viggo, Sujita Pal, Sheikh Syed Ali, Sami Chaudhary, Arnab Chakraborty, Abhirup Datta, Nirupam Roy, Madhurima, and Pasun. So we want to do intensity mapping with the 21 centimeter line in this post-reionization epoch. And this slide is a different slide than what you have, similar slide than what you have shown these 5 days. The CMBR, then the dark ages, then the epoch of reionization, and here is the post-reionization epoch, which I am focusing on. So we want to see a part of the sky with a single dish telescope or an interferometer, and we want to, with an interferometer like GMRT, we want to see the brightness temperature fluctuations due to the 21 centimeter signal. And there are other things which are the foregrounds which emit at the same frequency as the redshifted 21 centimeter signal. And we want to separate, my goal is to separate the signal out from the foregrounds. So the data that I have used is, there is a summary of the data, and this data has been analyzed and presented in detail by Chakrabarty et al. In this paper. And we have taken a 24 megahertz bandwidth from the data at the central frequency of 432 megahertz, which corresponds to this redshifted 21 centimeter signal from this 2.28, z is equal to 2.28, and this is a high. This has been taken with a high frequency resolution. So what the statistics that I want to consider is the multi-frequency angular power spectrum. It is defined in this way. So we have this brightness temperature fluctuation in the sky. It is in the all direction and in different frequencies, and it is written in terms of the angular multipoles, and we cross correlate the angular multipoles at different frequency to get the multi-frequency angular power spectrum. And in this small bandwidth that I am considering, the signal can be assumed to be ergodic, and we only the thing that matters is the separation between the two frequencies, and this quantity CL delta nu is what I call maps, and this is what we estimate. So a little deviation, what is the expected 21 centimeter signal at these redshifts? So in this post-Reionisation epoch, the expected 21 centimeter signal follows the matter power spectrum, okay, and through a Fourier transform we can get the decorrelation properties of the 21 centimeter signal. And if you see at a fixed angular multipole, the signal decorrelates faster, decorrelates quite faster, and within 1 megahertz the amplitude of the signal falls 90% from its peak value. So this black line shows where the signal falls to 90% from its peak value. The blue line shows where it falls to 60%, and this is similar for a larger L, except the fact that it falls even faster. This is because the 21 centimeter signal is a line emission, and it at different redshifts it follows the matter power spectrum. And the foregrounds, on the other hand, they are from the continuum sources, and it is expected that they will be correlated across this whole delta U range. So this is from one L from the measured data, this blue curve. The idea is that we model the foregrounds in this region where the 21 centimeter signal is whereas the 21 centimeter signal is expected to be localized in this small region. So we model the foregrounds in this region with a polynomial and extrapolate the polynomial in this region. We apply the same thing with the expected 21 centimeter signal to check whether we are losing any signal, and we have to quantify whatever the signal loss is that, and we incorporate in our analysis. And to estimate this CL delta nu from the measured visibility data, we have used the tapered grid estimator, which Professor Bhardwaj has previously explained in day 3. Okay. And this idea of modeling the foregrounds from this region and extrapolating it back here was first presented in Ghosh et al. In this paper, so you can also check that. So when we apply that, we get, okay, we apply that on different L values, and we check the residuals, and you can see that the most of the residuals are consistent with the noise level. These are 2 sigma noise levels, and we compare these residuals. We apply the same, as I've said, we applied the same thing on the signal to check for the signal loss, and when you compare them with a maximum likelihood, we can constrain this 3 parameter omega h and bh1, and we have put an upper limit on the parameter. We have divided the data in 3 sets and also combined them, and the tightest constraint we get is around 0.02. The value of omega h1, upper limit on the omega h1 and bh1 is 0.02, and they are all coming from the noise level. And when we check the cylindrical power spectrum, this is what is shown when we have not removed the foregrounds, and this is after removing the foregrounds. And we can see that the wedge-like features or the foreground dominated modes are now free, and we can use this whole k perpendicular, k parallel modes to estimate the 20 centimeter signal. And we have checked also the noise statistics of this data, of these values, with this quantity x. Okay, so x is, sorry for that, I have not defined it. So it is the power ratio between power spectrum and the expected noise level in the power spectrum, and it is a symmetric function which indicates that we have mostly dominated by noise, and it fits well with the Gaussian, with a Lorentzian. And we then calculate the cylindrical power spectrum, and let's focus on these two lines. The orange line is what we get when we use the foreground avoidance, and this red line is what we get when we use this foreground removal. And the best limit we get is around 21 millikelvin square. And there is a summary of the results. And the best limit on the omega H1 BH1 is 0.02. So this is the summary. This is the intensity mapping is a promising probe where the primary challenge is foreground, and we use we try to remove the foreground by considering that the 21 cm signal decorrelates faster than the foreground, and this is the best upper limit, but you still have to go 10 times deeper than this. Thank you.
Next speaker is Rashmi Sagar.
So, hi everyone, I am Rashmi Sagar from IIT Indore. First of all, I want to thank to the organizer for giving us the opportunity to present our work. So, this is our first work, which I have done with in collaboration with Abhirup, Arnav and Akriti. So, this is the first slide, which is very common. So, I am going to skip this slide. So, we know that there are different kind of challenges in detection of 21 centimeter signal, in which mainly three are astrophysical challenges, instrumental challenges, and this computational challenges, in which in astrophysical challenges the main challenge is the foreground, which is 4 to 5 order higher than the 21 centimeter signal, in which there are many kinds of foreground, which are galactic synchrotron emission, point sources, free emissions. So in which the dominant one is galactic synchrotron emission. So the motivation behind our work is to characterize the property of this galactic synchrotron emission, and so that we can properly get which kind of these foregrounds, and we can properly remove it in order to detect the 21 centimeter signal, or to set the upper limit for that. So here we have used the updated GMRT in band 2, which is 120 to 250 megahertz. Here we have taken 24 hours of data, and the frequency, the central frequency was 150 megahertz, but after the calibration, after the flagging, we found that the central frequency was 183 megahertz. So we have actually studied the LIS N1 field here. So we have use the direction dependent calibration in band 2, and we have collected all the calibrated visibilities, and in WS clean we have found this image. So here you can see the central region of the image we have received. So you can see this is the whole image after the primary beam correction. The RMS noise of this image is 233 microjansky per beam, and the dynamic range is 7500 at the central frequency of 183 megahertz. So these are some source montage which you can see that from the images I have taken, and we have compared it with other UGMRT at different frequencies. So these are some you can see. So here we have done the source classification. We have generated this catalog from PyBDSF of 1232 sources, and we have done this how many resolved sources and unresolved sources using this Frazen et al. 2019 at 3 sigma. And here you can see the resolved sources is 409, and the unresolved sources is 823. And we have also check our catalog while doing this comparison of flux offset in comparison with other catalog like LOFAR, UGMRT at 400 megahertz and 610 megahertz. We have also done the positional accuracy for our catalog using the condition of SNR greater than 10 sigma, where sigma is nothing but RMS noise, which I have told you. And this the condition, the other conditions are the source should be isolated and compact sources for both. So we have also calculated this spectral index for this catalog we have generated. And then we have also find out this normalized differential source count. Here you can see in the red points for our catalog, and for other colors for other catalogs at the other same at the other frequencies in the same field, or also the Lockman hole at 325 megahertz using GMRT. So other than image analysis, we have done the Fourier analysis, in which you have already heard about the TGE, which is the visibility based estimator. So we have actually compared here the two estimator, which is visibility based estimator and image based estimator. So people who are interested in image based estimator, we can have a discussion at FC 43, sorry 23, and we have actually compared these image estimator and visibility estimator, and you can see the results for the amplitude and the slope. So these are for the angular estimator, angular power estimator for the residual.
Last 1 minute.
Yeah, sure. So the upper graph is for point source, where you can see it shows a Poisson distribution pattern, and in residual you can see the power law in both plots. And here we have compared these both plots using image based and visibility based, where image based can actually retrieve these low multipoles where the taper gridded estimator can't do. So I am up for discussion. If people are interested, please visit FC23. Yeah, thanks.
Next speaker is Dashin Krishna M.
Okay, so I'm here to present my work with Mayuri on constraints and instrument systematics for CMB spectral distortion experiments. So we know the recombination is the period of the formation of first atoms. So it happened during a redshift of around 500 to 8000 with a series of step-by-step reactions. And we know that with computation, we expect a series of ripple-like distortions, which are very unique spectral features in the CMB spectrum, underlying CMB spectrum. So Apsara is an experiment, ground-based experiment, trying to detect these recombination signals in 2 to 6 gigahertz frequency range. So this is the expected sky spectrum at the frequency range which we are interested in, 2 to 4 gigahertz. And the right side, the signal is from the computed signal from the Cosmos spec. This is a recombination signal, how it looks at in the frequency range, 0.1 to roughly 1000 gigahertz. And we are trying to detect in 2 to 4 gigahertz frequency range, which we can see. Mayuri also explained there are 2 unique ripples which we are trying to detect. So the main motivation for our work, so in the Apsara is actually expected to observe with 255 days with 128 RF radiometers to get a confidence around 90% detection, confidence detection. So this thing is estimated with an ideal instrument and ideal systematics that are possible. The main motivation for this work is the instrument is generated systematics that can affect the signal, how it can distort the signal, how it can reduce the confidence of detection. So, can this detection be practical in an actual experimental case? So some of the systematics and their effects are explored in this work. So the rough main method which we do, we generate the sky spectrum with the galactic emissions CMB and the added recombination lines from the template which I have shown. And we are trying to use the smooth function fit and try to remove the smooth part, which is basically the foreground and the CMB emissions. And the residual which we get is of the order of nanokelvin, as we can see. So the red one shows the computation with the added recombination line, and the blue one without the recombination, just the null case, just to get an view of how the smooth function can get the residual, because other two, the galactic and CMB emissions are not, they are very smooth. So now we are trying to change some antenna parameters, perturb the characteristics of the systems, and we are trying to get the residual. And for comparing the two residual, we are using this is the Euclidean distance between the two residual and the Fourier analysis. So some of the systematics which we are trying to explore have given kind of animation. So you can you can see here varying frequency and how the beam wobbles in one direction, how it changes from the with respect to frequency. And the right side part, you can see how the beam stretches, again with difference in frequency. All these things can happen in an actual instrument. In fact, they can happen all together at a time. So it's kind of mixed. So we're exploring this thing, how it affects the signal. So basically here I have mentioned the Euclidean distance between the two signals. The red one is the actual ideal case signal with an instrument without any systematics changes, and the dotted line is the perturbed case, how we change the wobble angle here. So as I am changing the wobble angle, how the instrument affects how the residual gets distorted for the whole analysis. So here I have mentioned the Euclidean distance, and we can see beyond a certain point the distance increases, as we can see from the graph also. The signal is distorted so much so that we cannot recover the signal back. And this analysis is I have shown only for the beam wobbling case, and this analysis is done for other cases also. And other than the antenna beam wobbling case, we have also
Last 1 minute.
Yeah, we have also looked at the antenna S11 characteristics, how it looks. So here I have just some model antenna with 2 resonant dips, and I am basically varying the small fluctuations which are possible in the S11. This can affect the how it can affect the signal. So this is the kind of residual which we get. The red one is the ideal case, and the dotted one is the perturbed case. As we can see, the residual. This is the residual when we have the fine features to be of order of 10 power minus 6 decibels, which we see is very small compared to the actual the real possible case. So if we go, if the ripple order is of a higher magnitude, then we cannot get back the actual signal. So these things can affect our detection. So some of the conclusions which we can take is we don't need an ideal instrument for our analysis for the experiment. We can have some non-idealities, but within certain constraints that are possible. And even antenna return loss, the only thing that matters is the smaller fluctuations. As far as we can model the higher order things well, the factor which matters is the smaller fluctuations. And this kind of analysis, we are using it to for designing the experiment, designing antennas, and then checking out our analysis. And this technique can also be used for experiment focusing on dark cages and others. So, thank you.
Our next speaker is Fazlur Rahman.
Hello everyone, I am Fazlur Rahman. I am a final year PhD student at Indian Institute of Astrophysics. So first of all, let me thank the organizers for giving me the opportunity to present my work. So this is the title of my talk, Morphological Statistics of Galactic Synchrotron Emission. So this work is done with my collaborators Prava and Tuhin. So yeah, I don't think that no one is going to disagree with me on this thing, foreground challenge. So in the context of CMP, so this is the challenge we have, like so this plot is for temperature and this is for polarization. So the overall thing is that improved foreground modeling is crucial to capture tiny signals from the early universe. Okay, so in this work, so we are focusing on galactic synchrotron. So here I have given the famous Haslam map for 108 megahertz. So in CMB, as Tuhin was telling in the first day, so mostly, so this is the Haslam map, and so we use a spectral index to go to the frequency bands relevant for CMB using this spectral index. So one thing that I want to highlight is that while modeling synchrotron emission, so it's a it's always approximated as Gaussian and isotropic at small scales. So in this work, what we are doing is we are trying to test the validity of this approximation and explore the small scale statistics of galactic synchrotron emission. Okay, so our methodology is like this. So we study the non-Gaussianity and statistical isotropy of Haslam map at different sky regions and angular scales. Also, we explore the frequency dependence of these features by studying high frequency bands which are relevant for CMB. Also, we extend this formalism to other synchrotron maps, mainly the synchrotron maps which are obtained as the component separated maps from Planck and WMAP. So the main motivation is to search for residuals in these clean maps. So for this, we use Minkowski functionals. There is an S missing here. So these Minkowski functionals are real space statistics. It encode the morphology, non-Gaussianity, isotropy information of random fields. So the main thing is that it has information of all higher order correlations, unlike the 3.4 point standard methodologies. Also, it's based on escalation formalism. So, given a random field, we can make escalation set or level set, and Minkowski functionals prove the geometry, isotropy, and count of these structures. So, these are the three scalar Minkowski functional: area, fraction, contour length, genus, and we also use Minkowski tensor, one of the Minkowski tensors called contour Minkowski tensor. So, this can capture the information of non-Gaussianity as well as isotropy of any random field. So what we do is okay, so before going to the analysis, so we do some pre-processing steps. So as usual, we mask the galactic region, and also we mask the high emitting regions in the sky. Also we wanted to mostly focus on small scales, so we remove the large scale fluctuations. Okay, so let me come to the results. So this is the Haslam results that we have. So we have the Minkowski functionals for Haslam map here. So we can see that the synchrotron field is mildly Gaussian at smaller angular scales. So the data points are matching closely with the shape of what is expected for a Gaussian random field. Okay, now the interesting thing is to understand the non-Gaussianity, we defined a quantity delta V, which is the deviation of Minkowski functionals for a non-Gaussian field. So these are the deviation function delta V0, V1 and V2 for different masking sky regions. So we see that if we do more masking, the amount of non-Gaussianity is decreasing. Also what we did is like we remove the large scale fluctuations and we went to smaller scales. So the overall conclusion is that if you do more and more, we are throwing away more and more large scale fluctuations, we are going to small scales, then the non-Gaussianity is decreasing. So these are matching with the initial approximations people take, that if you go to small scales, the non-Gaussianity is decreasing. However, we find that the amount of non-Gaussianity at the Haslam resolution is not low enough to model as Gaussian. We found a 3.3 sigma non-Gaussian deviation in it. Okay, finally, another interesting fact is that there is a characteristic shape for these three functions. So this shape is that of a GNL type non-Gaussianity. So in the context of CMB, people have already studied how the GNL non-Gaussianity look like for Minkowski functionals. So this has a characteristic shape similar to the GNL non-Gaussianity. So next thing what we have done is we have repeated this analysis for other synchrotron maps. So like we have studied WMAP synchrotron maps, which are the byproduct of the component
Last
separation.
1 minute.
Sure. Byproduct of the component separation methods like MEM, MCMC. Also we have used the Planck maps and beyond Planck maps to study how the features we have found already is whether they are repeated in these maps, etc. So we find that okay, there are significant deviations for the Minkowski functionals V0, V1 and V2 at different angular scales. So this could be indicating that okay, there is the presence of residual foregrounds. For example, it's well known that in WMAP synchrotron maps, the presence of AME is reported. Also, there could be unresolved point sources or instrumental systematics which were not taken care. So also the last thing that I want to highlight is that so even for Planck and WMAP synchrotron maps, we are finding that characteristic shape which we found for Haslam repeated. We have done the same analysis with thermal dust emission and anomalous microwave emission. These are the other major foreground maps, and we find the characteristic shape similar to that. So this is the summary. So we find that okay, at the Haslam resolution, the level of non-Gaussianity is not low enough to model as Gaussian fluctuation. Second thing, the kurtosis nature of non-Gaussianity shows the importance of morphological tools in scanning residuals. Also at small scales, the synchrotron maps show large morphological differences, indication of residuals in clean maps. Also, we are thinking that the kurtosis nature as a generic feature of different foregrounds at small scales. It could be extended as an application in non-Gaussian foreground modeling. So thank you. So this is my poster number. Please do visit.
Our next speaker is Sarvesh Mangala.
So I am Sarvesh, and I thanks the organizer for giving me an opportunity to present my poster here and to present my work. And this is the to probing low latitude ionosphere using the GMRT. And during the conference discussion sessions and all those things, very few of us are concerned about ionosphere. I'm very happy that my collaborator and my supervisor Abhirup is a total supporter for ionosphere, and like ionosphere created problem in the radio data. So let me give you a short description about the ionosphere. So the ionosphere is the ionized plasma that reaches from 80 to 1000 kilometer overlapping into the mesosphere and the thermosphere, and it shrink and it it shrink on the condition of solar radiation, and each ionospheric layer is depend upon the solar activity, and it changes with day to night time cycle, seasonal and solar activity. There are various phenomena that are present in the ionosphere, from large scale disturbances to small scale disturbances, and there are also ionospheric scintillation that create a lot of problem during the calibration procedure. So for calibration, Longstale discussed 4 regimes based on the conditions, based on 3 parameters, that the scale size of the array, the scales of ionospheric fluctuations, and the projected field of view of your antenna at typical ionospheric height. So till now, all the radio telescopes that have been built are coming into regime 1, 2, and 3. But now we are making bigger and bigger telescopes, and also at low frequency. So we are coming into regime 4, and where the ionosphere is quite an obstacle. Believe me, it is. So you all know about radio interferometer, how it take data, measure visibility, and you do the calibration. But at low frequency, there are many challenges. The ionosphere is one of them. But interferometer measure differential phase between antenna pairs. So you get differential tech. Tech is just a measure of ionospheric activity, and so if you get the calibration solutions, so I have only plotted here northeastern arm for GMRT, and you see there are some fluctuation. This is nighttime, and this is like dawn and sunrise. Sorry, in the coming years. Sorry. So these are the northeastern arm, and you can see this following the same pattern along their direction, but also scaling with the baseline length. So, and also their small scale fluctuations are in the night time, and high um, um, longer period fluctuations are also. Don't just. I'm very nervous right now. I'm so sorry. Why? So the smaller scale fluctuations that are present in the night time are also so in the daytime it is not, your data is secure. So in the night time also there are fluctuations that are corrupting your visibility and all. So how these ionospheric variations can be detected, and how are these big these structures, in which directions they are moving, and at what smaller structures that are present in the ionosphere. So I don't want to go into detail, because you can come to my poster. Please come to my poster, and but I want to give you a spoiler that GMRT can detect up to till 10 kilometer of wavelength of ionospheric fluctuations. But for future, expect that we can go to moon, yes, but the calibrations, all those things on the ground-based telescopes needed to be done. And so this I know that GMRT is located in the low latitude region, and it is majorly affected by the ionosphere, but the mid latitude telescopes are also affected by the ionosphere, and as they are making bigger and bigger telescope, the same scene, but as sun is going toward the solar maxima, these calibration needed to be done in real time. So thank you.
Let's thanks all the speaker of this session again.
And we're going to go frontiering in the sense of even more other aspects of frontiers in just general astronomy and cosmology, and frontiers in cosmology by looking at new wave bands beyond just our familiar 21 centimeters and CMB. So we're going to kick it off with gravitational wave astronomy, one of the new frontiers certainly in all of astronomy. Ajith, turn it over to you. Ajith.
Thank you. Good afternoon. It's a great pleasure to talk to you today. I'm very grateful to the organizers for this kind invitation. I'm also very sorry that I had to miss the entire conference practically. I was indeed hoping to attend the entire one, but unfortunately, due to an emergency, I had to travel the last few days. So today, I'm going to give you a brief overview of the sort of current status of gravitational observations and what we can expect in the next decade or two. And by even looking at different wave bands, not only the high frequency range that is probed by the current observations by LIGO and Virgo. And just to recap, I'm sure all of you know that the first direct detection of gravitational waves happened in 2015 by LIGO, and this was the observation of gravitational waves from a binary black hole coalescence. These are, to everyone's surprise, this was a rather massive system of binary black holes and came from about a 400 megaparsec away. And this was one of the loudest signals that we have detected so far. Still, we have detected some louder ones so far. So in the last 3 years, during the last 3 observing runs, Virgo joined in the meanwhile, and LIGO and Virgo have observed order 100 gravitational wave signals from different compact binary coalescences, most of them being binary black hole signals. But we also had a few detections of double neutron stars as well as mixed binaries, including 1 neutron star and 1 black hole. And here is a cartoon version of the compact objects discovered by LIGO and Virgo through their gravitational observations, and contrasting them against the compact objects discovered by electromagnetic observations. The vertical axis here is the mass of these objects in solar masses. The horizontal axis has no meaning. And each cluster corresponds to 1 gravitational wave event. The cluster in blue or these orange ones. And you start with a binary system which merge to form a more massive compact object, which is almost always a black hole. So these blue ones are the binary black holes observed by LIGO and Virgo. And this, for example, this cluster corresponds to 1 particular event where 2 black holes of about 25 and 40 solar masses merge to form a remnant black hole of order 60 or so. And these orange dots are the neutron star observed by LIGO and Virgo through their gravitational observations. And in contrast, there are some interesting mixture of blue and orange. And at this point, we cannot tell whether these are indeed black holes or neutron stars, because currently our classification is purely based on the mass of these compact objects. And if you are in between order 2 and 3, one could go either way. So one could have proposed situations in which you could form light black holes or even massive neutron stars. And if you contrast these with electromagnetic observations, these crimson dots are the black holes discovered by X-ray observations from our own galaxies through X-ray binaries. And these yellow dots are the radio pulsars. And one fact is very apparent, which is that LIGO and Virgo seem to discover a lot of massive black holes. And this is what I said was a surprise, because very conventional means you were expecting that most of the astrophysical stellar black holes were order 10 solar mass, like the ones that we have seen in the universe. And it turns out that there are other populations of black holes which we did not know to exist until then. This presents some questions to the the massive evolution of massive stars and how you produce these heavy mass black holes, etc. And there are different ideas. Of course, even with it is not totally difficult to produce this heavy mass black hole for the collapse of massive stars, but also other ideas such as primordial black holes are very much back in game after these observations. And it's very hard to summarize all the science in the next 10 minutes or so, but I will just very briefly summarize some of the highlights that came from these observations in the last 7 years or so. These are indeed the first detections of merging black hole systems, and they also provided evidence of these rather massive stellar mass black holes, order 30 solar mass or even higher. there is one potential evidence of an intermediate mass black hole system. This particular merger, which is a very, very short gravitational signal, seems to be produced by a compact binary system of total mass about 150 solar mass. So this must have produced a remnant black hole of order 150 solar mass, which is in the traditional band of intermediate mass black holes. This was a spectacular observation of a binary neutron star producing gravitational waves as well as electromagnetic signals across the spectrum of electromagnetic waves, starting from gamma rays all the way up to the radio, which produced a fantastic amount of very interesting science. There has been additional detections of at least candidate binary neutron stars or neutron star black hole binaries. I said candidates because these classifications are entirely based on the masses of these objects. We did not see any electromagnetic counterparts for these objects. There could be multiple reasons. First, that they are rather far away, these sources, as compared to these famous GW17-0817s, which would have made it harder to detect these electromagnetic counterparts. And also the sky localization of these signals were actually very poor, because either these were only 2 detectors are operating or so. So, or it could be also possible that some of these high mass ratio objects like neutron stars, black hole binaries with large mass ratios would not produce any electromagnetic counterparts, because the tidal disruption would happen inside the ISCO or the black hole. So there could be multiple reasons for that. There is this very intriguing object, intriguing signal, GW190814, which was produced by a large mass ratio system, about a black hole of order 25 solar masses merging with a compact object of order 3 solar mass. And it is not clear what is the nature of this small compact object. In either way, it's a world record. It could be either the lightest black hole ever observed or the heaviest neutron star ever observed. These observations enable us to do the first tests of GR in the regime of extreme gravity and velocities. Just before merging, these compact objects will be moving with speeds close to the speed of light, and this involved tremendous nonlinear effects in the space-time also. And so far, all the observations are consistent with the predictions of Einstein's theory. Our ability to test GR is rather limited, because it is very hard to make accurate predictions on specific alternative theories of gravity due to multiple reasons. Starting from many of them won't even admit well-posed initial value problems for people to simulate and predict signals. But to the extent possible, one is able to at least ask the question whether the data is consistent with GR or not, by either artificially perturbing around the GR model and constraining these sort of perturbation parameters and ask whether their values are consistent with being 0, or do some kind of internal consistency test. For example, if you have a long enough signal, you can measure the properties of these black holes from the in spiral part of the signal, and using GR calculations, GR numerical elliptic simulations, you can predict the properties of the final object, its mass and its spin. And you can independently measure the properties of the remnant by looking at its ring down modes and ask whether these two estimates are consistent. So all these tests have resulted in being consistent with GR. Also, one could look at the propagation effects, whether this gravitational waves have any dispersion or not. In GR, gravitational waves are non-dispersive. And one way the gravitational waves can get a dispersion is by graviton having a mass. And the non-observation of this dispersion can be used to put an upper limit on the mass of the graviton. So that has resulted in some interesting upper limits on the mass of the graviton. A very nice measurement of the propagation speed of gravitational waves was possible by this multi-messenger observation of this GW17-0817, the neutron star merger. The fact that we observed gamma rays as well as gravitational waves with a very small time delay, order 1 second, even after traveling about 40 megaparsec, has concluded that the speed of gravitational waves is equal to the speed of light within a fraction of 10 to the minus 15 or so. So I understand that this has a lot of implications in the alternative gravity models invoked to explain dark energy, etc. And this has ruled out a parameter space of several a significant fraction of the parameter space of many alternative models of gravity. We have made the modest first steps in doing cosmography using compact binary coalescence standard sirens. The idea is that you can estimate the luminosity distance to gravitational wave sources accurately using GW observations. Not very precisely yet, but it is accurate without relying on any cosmic distance ladders. And if you have other means of measuring the cosmological redshift, such as from an electromagnetic counterpart, you can build the Hubble diagram. So far, we have one data point in the Hubble diagram using this bright source, and it has produced a posterior on the Hubble constant, which is currently consistent with all the different measurements. But we hope to see that with the upcoming observations, these precision would improve, the error bars would decrease, and one could contribute to resolving the existing Hubble tension. And even in the absence of electromagnetic counterparts, one could do cosmography using statistical methods, using binary black holes. And that also has been pursued, and again, we have very modest measurements so far, which will improve in the next years. We have seen interesting effects of gravitational waves themselves. For example, we have seen the effect of multipoles of gravitational waves. The gravitational radiation is quadrupolar in the leading order, but we expect higher order multipoles, and at least two events which large mass ratio both we have seen clear evidence of the higher harmonics of gravitational waves. And the electromagnetic observations following up this remarkable neutron star merger have hinted on the possibilities of the synthesis of heavy elements from the art process from the this kilonova ejected, produced by the nuclear ejecta from this neutron star merger. With the numbers increasing, the number of events increasing, we are also starting to do population modeling, starting to construct the mass function of black holes, what are their spin distribution, etc. And there are possible hints of things like a mass gap, high mass gap due to the pair instability of supernova, etc. And these are, one has to take these current constraints, in my opinion, with a pinch of salt, but there are interesting hints coming out, which will be either confirmed or refuted with upcoming observations. There are one surprise as far as the spins of, there are many surprises. One is from the mass of the black holes. That's again, most of them turned out to be more massive than what we thought they would be. And also, some kind of traditional wisdom was that these black holes would be rather highly spinning, because that is what is seen by the X-ray observations from our own galaxy. But it turns out that within our measurement precision, it turns out that most of the black holes producing gravitational waves are weakly spinning. This was a surprise, another surprise. So one has to wait for more observations to see how these population properties, the claims seem to be, they would remain robust with more and more observations. So I should remind, in fact, I don't need to remind the audience that the gravitational wave astronomy is only begun, and that's why there's a future talk. This shows, for example, how the cumulative number of detections is increasing with the effective space-time volume probed by these detectors. And one nice thing about gravitational detectors is that they are directly amplitude detectors. So a factor of 2 improvement in their sensitivity means a factor of 2 improvement in the horizon, and a factor of 8 increase in the volume, and hence a factor of 8 increase in the detection rate, assuming that sources are distributed uniformly in volume. So you see a steady increase as a function of the space-time volume probed by these observations, and the detectors are continuing to improve their sensitivity. The next observing run by LIGO and Virgo is expected to start in a few months, by May or June, where Kagra, the Japanese Kagra detector, will also join with a very modest sensitivity. Within a few years, we also hope that LIGO India will also be operational. This is a rough timeline that was proposed a few years ago, but because of the pandemic and other situations, all the timelines have slipped. And I should also say that in particular for LIGO, there is a whole set of upgradation plans with different levels of maturity. So the advanced LIGO is what we used to call advanced LIGO is what we call this, O4, the next observing run, where these detectors would reach their design sensitivities as planned by the original advanced LIGO concept. But then the next observing run will be in a new configuration called O5, which would have higher laser power, squeezed vacuum, bigger mirrors, etc., which is also funded. So this is also funded in the US with partners in Europe. There are concept proposals to upgrade these instruments further, and it's called the A sharp. And the next or half generation, 2.5 generation concept is called Voyager, etc. They all involve using the existing facilities, existing vacuum tubes, and put better detectors, including better masses, better test masses, better mirrors, higher power laser, better coating to minimize thermal noise, more squeezed light, etc. So they all incremental upgrades of the existing detectors. And with these detectors progressively increasing their sensitivity, we hope to do a large amount of interesting science. And so we can very confidently expect that in the next few years we will be detecting hundreds to a few thousand gravitational waves, really expanding the population. So one could really ask questions like, how does nature forms binary systems of black holes, which is totally an open question at this point. What is a black hole mass function? What is their spin distribution? Are these black holes astrophysical or primordial? And one could significantly improve the precision of probes of these strong gravity. Is GR the really final theory? Are these objects indeed black holes? Do we see any evidence of the black hole horizon? Or are they something more exotic? Theorists have come up with all kinds of exotic ultra-compact objects which can mimic a lot of signatures of the gravitational wave signal from binary black holes. But once you are able to probe much more deeper, then one can distinguish some of these possibilities from gravitational observations. There is very interesting impact on the nuclear physics. What is the equation of state of matter at extreme densities? And this can be observed either from the tidal deformation of neutron stars during the late in spiral in a compact binary system, or by looking at the post-merger oscillations from the merger of two light neutron stars. They both contain very interesting imprints of the equation of state of nuclear matter. We hope that with the increasing number of multi-messenger observations in particular, one could improve the precision in doing cosmography, as well as by combining a large number of these dark sirens, which does not produce any light. These are all sort of, in some sense, sure bets with some level of surety. But then there also, one is anticipating a large number of new phenomena also. For example, the detection of stochastic background produced by all the astrophysical mergers is imminent, because we have now measured the merger rate of compact binaries with some precision. Of course, there's some uncertainty in what is the distribution of these compact binary mergers in Redshift. Depending on this uncertainty, we will be observing the stochastic background produced by all the mergers within a few years. One could see very interesting new phenomena such as the gravitational lensing of gravitational waves. And again, this is something has to happen, and we know roughly the optical depth. And once you observe sufficient number of events, like order 1000, observation of strong lensing of gravitational waves become imminent. Gravitational waves also offer us to detect a completely new regime of lensing, which is in the wave optics regime, which is not possible in the electromagnetic waves. In the case of gravitational waves lensed by compact objects like black holes or other compact objects, the gravitational radius of the lens is comparable to the gravitational waves wavelength, because order a few hundred to few thousand kilometers. So we would see interesting diffraction effects, and so on. So, and again, there are new possible sources such as spinning neutron stars, galactic supernovae, etc. So I should really ramp up the speed. In particular about in this context, etc., the one big sort of upgrade to the current gravitational wave detector network that we are anticipating is to the joining of LIGO India, which involves building a LIGO detector in India. And the advantages are obvious because you are significantly increasing the baseline, which will increase the ability to localize sources, measure their polarizations, etc. Of course, when we started this with about like 10 years ago, as compared to the existing LIGO network, the improvement was dramatic. But even with Kagra, etc., joining, that's also a very optimistic plan because LIGO is Kagra is also very far from reaching their design goals. Still, the LIGO India detector can make a significant improvement. This is what you should have seen if the slides were very clear. However, so the bottom line is even if as a fifth detector network, LIGO India is going to make a significant improvement in the localization capabilities as well as polarization measurements. The status with the seed funding received a few years ago, LIGO India project has made significant progress. So these are the vacuum prototypes that was delivered last year and was tested. It passed all the requirements in LIGO. There is a site acquisition is complete. There is a site on-site building, and eventually we hope that the site will look something like this. This is the engineering plan of LIGO. And in parallel, all kinds of prototyping of optics and vacuum is in process. This is the vacuum. This is the optical system prototyping unit at the RRCAT. This is a clean room for staging and testing. There is a 10-meter prototype interferometer that is functioning at the RRCAT. There's a large computing facility that's already operating in Ayuka, etc. So to summarize, within the available budget, LIGO India project has made significant progress. And essentially, it is waiting for the big grant to start rolling out the construction. There are next generation, the community as a global scale is planning for the next generation of interferometers on the ground. So this could be either underground, which is the proposal from the Europe called Einstein telescope, using a triangular shaped detectors, or overground like LIGO but significantly longer arms, which is called the Cosmic Explorer. And they would significantly increase the sensitivity as well as the bandwidth, probing spectra close to a few hertz. And these detectors would practically observe all the binary black hole coalescence to the edge of the universe. So no one will be missed when these detectors will be operational. But also we know that we are so far only probing a very small region in the full spectrum of gravitational observations, the sort of high frequency band. And there are several efforts to measure gravitational waves at different frequency bands. To this audience, I don't need to talk about the CMB polarization. There is also this nanohertz gravitational measurements plan using the pulsar timing arrays, which seem to have even hit some gold. And these will be confirmed or refuted in the next few years. But there is also a plan of building, there is actually a funded plan for building a space-based detector called LISA with a launch date of about 2037 or so. And this is the noise spectrum predicted by that is anticipated in LISA. And they would observe supermassive black holes for months and even years, galactic white dwarf binaries, and some of the early in spiral of the stellar mass black hole binaries that is observed by LIGO, thus enabling even multi-band observations. You can combine different measurements or even provide early warning for LIGO by observing this early in spiral. There are more recently several interesting concepts for observing gravitational waves in the decihertz region, which is between the LIGO and LISA. And there are very interesting concepts with different levels of complexity and maturity, including like interferometers in space, interferometers on the moon, using the moon as a gravitational detector by measuring its resonant modes, by putting seismometers on the moon, etc. And they all are very ambitious projects, but different levels of ambition. But some of them more realistic than the others also. In particular, I want to advertise that there is going to be a discussion meeting in April at ICTS, our neighboring institution, which is my host institution, is on the lunar gravitational wave detection using the moon as a resonant bar to detect gravitational waves. It's really the original idea of Weber. Instead of using resonant bars of aluminum, use the moon itself as a gravitational detector. And in some sense, this is sort of aligned with a lot of space and lunar exploration plans of space agencies, including the ISRO of India. Okay, so I guess I'm run out of time, so I'll just flash my summary slides and take any questions.
Thank you, and we certainly do have time for a couple of questions.
So of course you mentioned the moon as the last thing, and this was also a talk given, I think it was last week at the Royal Society on exactly this here. So I think one of the questions that were asked then is, of course, right, we are also trying to go to the moon. There will be a lot of activity on the moon, right? Maybe even mining and all kinds of stuff, right? Radio telescopes being built. Is that going to disturb the moon sufficiently to prevent?
Yeah, so I haven't plugged in this community yet, but my understanding is there is some talk going on to divide the moon into the North Pole and South Pole. Give the moon and the North Pole to the miners and South Pole to the scientists and vice versa. Okay. There is some talk that is sort of starting to sort of organize activities in terms of their, disturbing each other.
But what you're saying is if that would happen, that would be preventing such a gravitational wave experiment on the moon. It should be more or less undisturbed, I guess.
Yeah, so you can only do this in the poles, either way. So if you sufficiently separate the mining activities and these quiet experiments to two poles, it is possible to do that. But it requires real consensus among different parties of interest.
More from the cosmology perspective, I totally understand why you would sell the H0 measurement as the main cosmology measurement. But if you indeed do, I think you call them bright sirens. If you do have lots of bright siren detections, you're actually mapping out the peculiar velocities. Peculiar velocities, because you have the redshift, you have the luminosity distance, so you're measuring the peculiar velocities directly. And you can do a lot of cosmology with that, apart from just H0.
Absolutely.
Sorry, maybe I misunderstood this, but why particularly the poles? Is it because of the spin of the moon that you can't detect gravitational waves if you're on the equator or something?
I honestly don't know. I have to ask. The current, it must have to do with some logistics, I would say. I don't know what the reasons are. I'll find out and let you.
I might ask about just the extent to which general relativity is assumed in many of the calculations, and how well can we actually test beyond GR if GR is being assumed in all of the waveforms.
Yeah. So I think one has to build on like different levels of trust. So the working assumption is that whatever deviation that we expect from GR is going to be like a small deviation from the GR prediction. So that is the case. If the true theory is GR, you will have some mismatch between the GR models and the signals, so that you will lose some signal to noise ratio. But the GR templates will be adequate in detecting these ones. Then one could follow them with some more precise parameter inference techniques and model selection to see is GR indeed the best fit template or not.
All right, with that, let's thank Ajith again. Okay, yes, great. So the next speaker will be telling us about one of the other frontiers, the very large telescopes, in this case the 30-meter telescope, the TMT, and in particular India's participation. So,
Disclaimer, I'm not a cosmologist, so whatever science cases I will give you glimpses of are all borrowed from the cosmologists in the TMT group. So in the next decade, there'll be three segmented telescopes, the giant segmented telescopes, two of which, the European Large Telescope and the giant Magellan Telescope, will be located in the southern hemisphere, and the 30-meter telescope will be located in the northern hemisphere. Although all three of them are segmented, amongst these three, the GMT has a slightly different configuration. It consists of 7 segments, each of 8 meters. whereas the ELT and the 30-meter telescope consist of several segments, each of in the form of hexagons, each of 1.44 meter along the edges. So the TMT will be constructed by the TMT International Observatory, which is an international partnership consisting of Caltech, the University of California, and Aura is also part of it. There's very significant funding from the Gordon and Betty Moore Foundation to the project. The other partners are NRC from Canada, NINS Japan, NAOC from China, and the Department of Science and Technology, Government of India. Also, the Indian participation is also funded by the Department of Atomic Energy. So what is the configuration of the TMT in a nutshell? It's a wide field Altaz RC telescope. As the name suggests, it is a 30-meter diameter primary consisting of 492 hexagonal segments, as I mentioned earlier. Each segment is 1.44 meter across the corners. At first light, it will have an active secondary mirror, and a flat tertiary mirror will beam the light to the Nasmith platforms. Two Nasmith platforms, so about 8 instruments can be made available at any given point of time. And these instruments together will cover all the way from 0.3 micron to the mid-infrared wavelengths. At first light, one will have the adaptive optic system in the near infrared called the nefarious, which will enable diffraction limited images at the J, H, and K bands, and this can feed up to 3 instruments. The dome itself is a rotating caloid enclosure. It's a small dome. It's just 33 meter the external radius, and this compact size of the dome provides better wind protection and preserves the seeing of the site. So where is it going to be located? The preferred site is Mauna Kea, and as everybody is aware, there have been certain issues, so the construction has been stalled, but there are efforts to resolve the conflict and move on with the project. But should that fail, the second site has been identified, and that is La Palma, and whatever clearances that one requires at La Palma have been obtained. But as of today, it's Mauna Kea at Hawaii is the preferred site. First light instruments, there will be three first light instruments, 2 of them in the near IR fed by the AO system, the nefarious, and 1 seeing limited optical instrument. The first infrared instrument is the IRIS, which will give diffraction limited NIR images, and it also has an integral field spectroscopic mode. This is covering the range of 0.84 to 2.4 micron, and it will have a field of view for the imager of 34 by 34 arc second at 0.004 arc second per pixel IFU. The next infrared instrument is the multi-objective diffraction limited high resolution spectrograph. This is also AO fed, and it will operate in the wavelength range of 0.95 to 2.4 micron. This has a 4 arc minute diameter field of view. The seeing limited optical instrument is the WFOS, which is a wide field optical spectrometer. It has a 25 arc minute square field of view, which is pretty big for a 30-meter telescope. And it has a 500 arc second total slit length. It's also capable of doing some amount of multi-object spectroscopy. It has a range of spectral resolutions, all the way from 1500 to 3500, with a goal of attaining a resolution of 5000. The next decade instruments, it's planned to have a ground layer adaptive optics through an adaptive secondary, which will be large enough to cover the field of view of WFOS. and also have a mid-infrared adaptive optics for the mid-infrared region. The other instruments which have been selected after an exercise of calling for proposals for the next generation instruments, which was done sometime around 2016 and 17. So these are the four instruments which kind of have been proposed as the next decade instruments. It's a planet finder, the planet formation instrument, MICHI, which is the mid infrared Eshel spectrometer, a high resolution optical spectrograph. This instrument is being, sorry, I think I can, yeah. The HROS currently is being led by India, and an IR multi-object spectrograph in the 0.8 to 2.5 micron region, which will have a larger field of view as compared to IRIS. So coming to the capabilities of the TMT, in the seeing limited mode compared to the existing 8-meter class telescopes, it'll have a gain of by a factor of 14. In the multi-conjugate adaptive optics mode, it'll have a factor of nearly 200 and much higher than that in the extreme AO mode. Obviously, it'll have a much better diffraction limited spatial resolution compared to the 8 meters, as well as the JWST and HST, obviously. The other capabilities with respect to the various existing survey telescopes and also the space-based telescopes. So these arrows here show the limiting magnitude or the faintest targets that can be detected by these facilities, and these vertical dashed lines here, they show what the TMT can achieve. So for example, in the seeing limited case, one is looking at V-band spectroscopy for a signal to noise ratio of 10 at a resolution of 1500. In 300 minutes, one can hit 26 magnitude. So TMT, in fact, will perform much better than the JWST in, for example, the Z-band spectroscopy as well as the Z-band imaging. And it will more or less hit the JWST limit in, with spectroscopy in the H-band. Coming to the angular resolution, this plot shows the kind of angular resolution that one will be able to achieve, and it's very obvious that the TMT with adaptive optics is going to give you the best angular resolution. So what are the science cases? These are based on the detailed science case documents, which was developed as a community effort, the international community effort in 2015, and updated in 2022. Obviously, being an observatory class telescope is going to cover the full domain, all the way ranging from the solar system objects to doing fundamental physics and cosmology. So it will provide us new frontiers of the known unknowns, and not to mention that there are a whole lot of unknowns which we don't know what will happen. So some of the key areas are, not surprisingly, trying to understand the nature of dark energy and dark matter. Are the physical constants really constant? What are the first objects that were formed in the universe and how did they form? We have heard a lot of this in this conference. So even the TMT will be able to address these questions. Coming to our own solar system, understanding our solar system, and also, are we unique? Is there life elsewhere? This is a burning question, which we hope TMT will be able to answer if JWST has not already done it before. And finally, the other interesting area is to understand the transient universe. So what are the progenitors of the most energetic transients, and how are the heaviest elements in the cosmos formed? So let me just give a glimpse of some of the science cases which I heard during this conference, and based on my own understanding of those as a non-cosmologist. So what is it that the TMT can do to some of the topics that were discussed here? Looking at the sources of reionization, the TMT will be able to contribute to this area. From what I understand, the galaxies in the range of the MUV of -13 to -18 produce more hydrogen ionizing photons in the luminous galaxies at a redshift greater than 7. However, as of today, the abundances of such galaxies is unclear. The JWST has already been providing new insights, and from whatever data has been obtained, it is seen that these galaxies at these redshifts are extremely compact. So it's not very clear as to what the morphology of these galaxies are, and as well as what their composition, the metallicity, and these sort of physical parameters are. The TMT will be very easily be able to resolve such sources with the adaptive optics system. So the morphology, one will be able to have a better understanding of the morphology of these sources, and hopefully a better understanding of the reionization. The other thing is that if one looks at the POP3 ZAMS burst, the predicted spectrum, one expects to see lines due to the ionized carbon, oxygen, and the carbon-4 in a redshift of 7 galaxy. Whereas the truly primordial galaxies will have helium, and these lines can be detected with the TMT near-infrared spectroscopy and the mid-infrared spectroscopy up to a redshift of 14. TMT will also be able to contribute to the studies of the Lyman break galaxies, which are like the high redshift counterparts of the low metallicity galaxies found in the low redshift universe. With its adaptive optics capability, they'll be able to resolve, and the lensed ones, particularly, one will also be able to do spectroscopy of these galaxies. One will also be able to study the baryonic structure using the TMT, and one of the key programs that has been proposed to be done with the TMT is doing a survey of the baryonic structure in the high redshift universe using the WFOS. And this table here gives an example of the kind of, the number of targets that one can study with a total of 1,000 hours of a survey. And such studies can also be used to understand the feeding and the feedback from the CGM or the IGM, and also to understand the relation between the growth of stellar mass and black holes. Something which will also help us understand the peak of the galaxy assembly. And this is a very familiar plot we saw several times in several talks during this conference. So these are some of the science cases of interest to the cosmologists which can be taken up with the TMT. One can also understand the quenching of star formation, looking at the formation of passive galaxies and also the birth of the Hubble sequence. Try to understand what are the modes of quenching by looking at the various traces. And with the TMT, one can probe these kind of objects beyond the local group, because one can easily go up to 26 to 28 magnitude per arc second square with the TMT. And finally, let me talk about the use of transients. The TMT is extremely well suited for studying transients, because one of the key requirements of the TMT is to respond to a transient within 10 minutes of the knowing that a transient has occurred. So one can easily study the GRBs and the GW sources as soon as the localization is known. And of course, the supernovae are always there, and it's extremely useful to study the very early phase of supernovae with a quick response. Of particular interest for cosmology is the study of type 1a supernovae as cosmological probes. We have heard about them. The TMT can be used for characterizing the high redshift supernovae and get a better understanding of these objects and their use as a standard candle. One will be able to do spectroscopy up to a redshift of 4 very easily, and combining the objects that you observe at the higher redshift with the ones at the lower redshift, there are a host of things that one can investigate and also look at whether there's a possible evolution of supernovae of type 1a with respect to the redshift, and also whether it's a particular subclass of the supernovae of type 1a which are really standard candles, because we have seen a whole lot of diversity in the type 1a supernovae, although they are seemingly homogeneous. This is because of the variety of progenitors which can give rise to type 1a supernovae and the variety of explosion mechanisms which can actually give rise to type 1a supernovae. So this is something that can be done. And with the core collapse supernovae, one can actually trace the high redshift universe, the star formation rate of the history of the universe, and also probe the initial mass function in the early universe by looking at the very high mass stars, the supernovae arising out of the POP3 stars or the very high mass stars. Likewise, the gamma ray burst can be used for probing the high redshift universe, way beyond what is being done currently. And this will be possible through the direct detection of host galaxies and the detection of galaxies in absorption along the line of sight to the GRBs, something like the quasar absorption lines, but using the GRBs because you can see them up to a much larger redshift, they being brighter, and also exploring the diffuse extragalactic background. The gamma ray burst can also be used as probes of the early phases of the stars and galaxy formation and their effect on the reionization of the universe. So just to give a summary of the synergy with other facilities, this table here gives the synergy with the ground-based facilities, and this gives the synergy with the space facilities, the current and the future. So all these green boxes indicate the various science areas and the synergy with which facility. What is shown here is that the dark green with the double tick indicates that these science cases have been referred to in the TMT detailed science case as well as in the science cases of those facilities. And whereas the single tick boxes indicate that it has been referred to in just one of the science case documents. So there is an excellent synergy with various facilities, which is what one would expect with such a large facility and an observatory class telescope. So let me come to the making of the TMT itself, and this is, as I said, it's an international partnership. See, all the partners are contributing to the making of the TMT. The philosophy of the entire partnership is that every partner, the 70% of the contribution that every partner is putting in is in terms of in-kind contribution. So the various systems have been subdivided amongst the partners. Canada will be is in charge of the dome and the adaptive optics systems, and also in the development of instruments. US is undertaking a good fraction of polishing of the segments and all the civil works, the integration, and of course the instrumentation. Japan is doing the telescope structure, it's supplying all the segment blanks, as well as polishing about 25% of the segments and also contributing to the instruments. China is doing the tertiary mirror and the laser launching system, but I'm not very sure about that now, and also doing some amount of segment polishing and contributing to the instruments. The Indian contribution is to supply the entire M1 control system, the hardware for the M1, that's a primary mirror controls, the software, which includes the observatory software and part of the telescope control software. We'll be polishing about 84 segments. We are contributing to the first light instruments and also to the next generation instruments. The coating chambers, the design as well as the manufacture of the coating chambers are also India's responsibility. So this is in a nutshell the Indian contribution. The mirror segments, 84 primary mirror segments will be fabricated for this, and we start with polishing the roundel, and this roundel, the polished roundel, is then hexed and then integrated onto the segment support assembly. Now, this initial round of polishing is done through a technique called the stress mirror polishing, and all the partners will deliver the hexed segment polished up to 2 micron peak to valley, which will finally be done. The final figuring will be done in a single place in the US up to 2 nanometer accuracy. So for the polishing, we have constructed a large optics polishing facility in our in the IAA's Crest campus. The polishing and the metrology equipment and process training has happened at Coherent USA. The equipment is arriving soon. And during this process, 2 roundels were polished at Coherent, and these 2 have already passed the conformance review. The hex cutting and pocketing process is under development. Coming to the segment support assembly, there are 82 different types which are needed, and total of 580 segment support assemblies. All of them will be manufactured in India. 5 have already been assembled by the end of 2022, and 1 has been shipped to the project for few further tests. The edge sensors, again, all the 3,284 edge sensors are going to be made in India. The initial edge sensors which were made have been qualified, but it's undergoing certain further development. It's an ongoing work still. Actuators, again, all the actuators will be manufactured in India. Each segment will have 3 actuators, so a total of about 1,500 actuators. These have been, the prototypes have been developed and successfully completed the environment tests. Likewise, the software development, the initial development has all been done. And the science instrument, we are contributing significantly to the first light WFOS instrument. There are various hardware design which has happened. So today, India is well matured to contribute with all its in-kind works, which in a way would not have happened if the project had proceeded on time. So thanks to the delay, we are well equipped today. A brief on the project status. Although there has been a delay in the construction, all the partners have continued with their commitment, including their own in-kind contribution. As all of you are aware, in the US ELT project ranked top in the US Decadal Survey, and based on this, NSF has started Environmental Impact Survey, and TMT has successfully completed the NSF PDR. NSF FDR is scheduled towards the end of this year. There are a lot of efforts towards resolving the Mauna Kea issue, and we're very positive that we will be able to. meet this revised project schedule, and TMT hopefully will go online in 2035. So, thank you.
Okay, certainly time for a question or two.
So maybe a short question on this issue on where the telescope is going to be. So if it's going to be on La Palma, does it also mean that Spain would join the program? Because as far as I understand it, most of the telescopes there have at least a 10% share from Spain. So would it become a partner in the program? And the other short question is, how would the change of the site impact the science? Because La Palma is of course not as good as Mauna Kea.
So regarding La Palma, Spain has been very positive, and they have offered the use of the office, the space in the institute in Canary Islands, and they have shown that the Spanish government was very positive of being part of the whole process, and even in getting the clearances and all that, there has been a lot of governmental support, although they are not officially a partner as of now. And regarding the question related to science, if we go to La Palma, the science which will be really affected would be in the mid-infrared, not in the other regions. Maybe in the ultraviolet, the extreme, the UV region that we are looking at, around 0.3 micron region, they will have some effect in that. But otherwise, because the seeing conditions are very similar, there's not going to be a major effect.
Thanks. So this is one comment on the table on synergies. I think there will be quite a few improvements possible from LISA and TMT. LISA and TMT.
I don't know if they've probably not mentioned that.
Yeah, it is not
LISA
mentioned. Yeah, so that, and also in the horizontal lines, there can be a few more takes of those surveys. So LISA can definitely be figured out here is a very huge overlap.
My guess is that LIGO slash because it says SMDH, it's not LIGO science. So it's probably LIGO slash LISA.
Yeah, I mean it's general GW. Yeah.
And it can be also on the other couple of boxes.
Right. Yeah.
Thanks.
Okay, with that, we'd better move on. So thank you again. And the final speaker in this session is Yashwant Gupta. I guess it'll take us a second. Upgraded GMRT, but it'll take us a second to load the talk.
Good afternoon to all of you. I start with the same disclaimer that the previous speaker did, that I am not a cosmologist. Worse than that, unlike her, she at least attended the talks in the last few days. I have not been able to do so. So I only have a foggy idea of all the exciting things you guys have been talking about just by reading the titles of the talks. But nevertheless, I will try to orient the talk as much as possible to cosmology, which you will probably start seeing some of the shortcomings of my understanding, rather than just talk in general about the upgraded GMRT and the SK, which I probably could. So, I start my cosmology with this diagram, which I guess most of you do, and when you are wanting to try to understand what happened from this stage when the dark ages ended and the first stars formed to somewhere. I don't know where you want to put your cutoff as where cosmologists stop doing cosmology and do normal things. Maybe when the solar system formed or something like that a few billion years ago. But then I put on my radio astronomer's hat and say, look, I want to study from there to there, and what's the best way to do it? Well, this is the best way to do it. If you can detect neutral hydrogen all the way across, then you are very well placed to be a good cosmologist. So that's what leads me to the question that which are the best tools for looking at neutral hydrogen across this vast reach of the universe, all the way from today to the epoch of ionization. And these are the two that I can think of. Fairly complete coverage with the upgraded GMRT all the way from 100 to 1450 megahertz, and nicely working facility. The other, it's crossed the artist's impression stage, it's now crossed the designer's table, and it's beginning to break ground and start building things. but it promises even much better capabilities than the upgraded GMRT, but we may have to wait till the end of the decade to see the fruits of that. So, with that, I start and talk a bit about the upgraded GMRT. So, the GMRT is, when originally built, was an array of 30 dishes, each of 45-meter diameter, located in the western part of India near the city of Pune. The GMRT, and I'll show you in a moment the configuration, has the 30 antennas spread out in a roughly Y-shaped configuration with a central core of 1 kilometer by 1 kilometer having 12 of the dishes and the remaining 18 spread out along these Y arms. And the main thing about the upgraded GMRT is the frequency range. I'll talk more in detail about this, which in the original legacy GMRT was very narrow parts of the spectrum that we could access between 150 megahertz and 1450. But what the GMRT offers is a very significant collecting area. And just we keep linking everything to SKA, but to the full SKA it's about a few percent, but SKA phase 1 it's just a little bit below the collecting area of SKA phase 1. And the important thing which makes the UGMRT really useful for cosmology is this, that when we upgraded it, we try to provide as far as possible seamless frequency coverage. Actually, we do go a bit below 120. You can go to 110 megahertz up to 1450, except for a couple of places where the interference from man-made signals is too strong to be able to operate there. And so what this does is two things. One, coupled with the fact that the maximum instantaneous bandwidth that we can process is 400 megahertz, it allows you to do high sensitivity continuum imaging, which may or may not be that much of interest, but it allows you the fidelity to probe redshifted neutral hydrogen all the way from today to the epoch of reionization almost continuously. And that is the main plus point, and I'll come back to that in a moment. So this is another way of looking at it in terms of the frequency coverage. The UGMRT is one of the best facilities in this part of the spectrum, and only the SKA phase 1 will do better than that at wavelengths of about 1 meter. And so the way the UGMRT is configured, just again a very quick look at the systems. So we split the total frequency range into 4 main bands. The lowest one, which we call band 2, going from 120 to 250 megahertz. Like I said, it actually goes a bit below 120, and then 250 to 500, 550 to 850, and then 1000 to 1450 is the band 5, which is the broad L-band system. And we transmit analog over fiber from the remote antenna locations to the central building, and then we have backends which can process 400 megahertz of bandwidth from all the dual polarization signals of 30 antennas to give you both the interferometric products as well as the beamformer products, which are more useful for pulsars and transients. And the GMRT legacy system has been operational since 2002. The UGMRT has been operational since 2019, and it sees users from all over the world carrying out different kinds of science. It's typically oversubscribed by a factor of 2 or more. And the range of science is quite vast, as you can imagine, for a general purpose facility, all the way from sun to extrasolar planets. And what I will focus a bit now is on the kind of things that the upgraded GMRT has been able to do in the area of cosmology and related topics. So start from the highest band, that is the nearest part of the universe. So this is a very interesting result that was produced about 3 years ago now using the band 5 system. The stacking of signals from about 450 galaxies with a mean redshift of 0.34. It also happened to be one of the deepest continuum images made with the upgraded GMRT at that time, and it led to the interesting result of a detection of the signal and useful inferences about the things happening at the galaxy evolution at that phase. Building on that, there's been similar detection by stacking more galaxies at further away redshifts, in this case mean redshift of around 1, which now falls in band 4, the next lower band of the UGMRT, and this was almost 8,000 galaxies, and this again within 100 hours of observation led to a clear detection, which has been further refined with the more deeper observations. And this again allows very interesting, and you would have heard this in much detail from Nissim earlier in the conference. And complementary to that, even detections of H1 in absorption, again from objects at redshifts of 1.2 or so, and this again actually was a bit of a serendipitous discovery, but it is what I think is the tip of an iceberg in the sense of lots of such objects that are probably within the reach of just the UGMRT itself, and not to mention the SKA. Moving from there, this again I think you have probably heard earlier in the week. This is the furthest redshift detection of H1 in emission aided by lensing, and this again is very exciting and interesting, reaching a redshift of 1.3. And once again, I think even the paper Chakrabarti and Roy estimate that there may be as many as 10 to the 4 such objects that will be within the reach of UGMRT, Meerkat, and probably more with the SKA, and this probably opens a new window to probe cold neutral gas at high redshifts. I would have actually gone from here to the next lower band, which is 300 to 500 megahertz. I don't have any results for that, but I think it's been talked about in this conference. I think Abhirup and his group have shown results on estimating foregrounds at those frequencies, and I think from IIT Kharagpur also you've had results on some of that. But jumping to the lowest band, which is where you would actually hope to detect the UR signal. The GMRT, even before the upgrade actually, was one of the first instruments to be put to work to try and make this detection. And really, I think he was here earlier in the week, right? So he led this effort when we worked together to use the GMRT in a very interesting mode where we used a pulsar as the in-field calibrator for calibrating the field, and produced some of the best limits on the detection of the UR signal at that time, which still I think compare fairly well with the new efforts that are going on. So that just gives you a flavor. Like I said, it's my flavor as of what kind of cosmology the UGMRT is capable of. And beyond that, like I said, what we are looking forward to is the SKA, which will take the sensitivity to the next higher level for across this same range of frequencies, which are interesting for cosmology. So I'll move from, then to talk about the SKA, and this is the SKA in a nutshell. I won't read out everything here because most of this will come in the subsequent slides, but it is the next of these large-scale radio astronomy projects in international collaboration. The full-fledged SKA is actually quite daunting when you look at its specifications. It talks about a collecting area of 1 square kilometer, which is where the name comes from, which is actually 30 times the collecting area of the GMRT array, with 3,000 small-size antennas with large fields of view, and antennas spread out to distances of the order of close to 1,000 kilometers. But linked in real time with optical fiber, and very wide frequency coverage, and radio quiet locations where you can really do the best job for the observations, and all kinds of cutting edge science. But what is currently being carried out is SKA phase 1, which has a reduced scope compared to this, but is still transformational in its possible impact. And so it basically would compare with all the other major facilities of which you've already heard about, the TMT and the LIGO. And the thing about it is, in terms of the science, again, you know, a very vast range of science topics, all the way from formation of first stars and galaxies to searching for extraterrestrial intelligence in the universe. And this is the full science case of the SKA as detailed a few years ago. And what you'll see, of course, is it's dominated by cosmology-related topics of various kinds. And of which I'll just show back to my simple cosmologist diagram, where the SKA mid and the SKA low will be probing very important regions of this cosmological evolution of the universe. So what it is, it's actually two telescopes, one to be located in South Africa and one in Australia, with the headquarters located in a third country, that is the UK. And as I said, it's completed the design phase, which itself took about 6-7 years to do. And the construction phase is just now started towards the end of 2021. And it will go at least till 2027, if not 2028. And then there is a phase 2, like I said, which is that full-blown thing that I talked about, which will be a decision taken based on the progress and the success of phase 1. So the phase 1, to focus a bit more in detail, has frequency range of actually now it's more like 50 megahertz will probably go till 10 gigahertz, and maximum baselines of up to 150 kilometers. But it will be done in such a way that all infrastructure that is being built is done keeping in mind that there will be an expansion to phase 2. And like I mentioned, 2 sites in Australia and South Africa. And this gives you an idea of the scale of what it is to cost for building the SKA. And so this is the location in South Africa where SKA mid, which will have parabolic dishes of 15-meter size spread out over 150 kilometers, and it's located in a radio quiet zone where man-made transmissions are kept under some regulatory control, and so that you can get the best results. And the SKA low is a slightly different design. It is actually dipole antennas, so cluster of dipoles, 256 of them make one station. So you can think of a station as an analog to a dish antenna, but it has more flexibility than a dish antenna. And then 512 such stations to spread out over 80 kilometers to give you the phase 1 configuration for SKA low, and going from 50 to 300 megahertz. And the global headquarters at Jodrell Bank Observatory in the backdrop of the classic Jodrell Bank dish, which is now fully operational as a headquarters. And the thing about the SKA is it really pushes the technology envelope in many areas, all the way from advanced and diversified antenna design principles to cryogenically cooled low noise electronics, and a very extensive fiber network in order to carry the data from all the remote antennas and stations to the central processing, and the computing, both real time and offline, required to process the data is equivalent to the best supercomputing capability that you could have available at that time, and all the clever ideas of big data machine learning that you can apply would find use over there. So this is to just give you an idea of the scale of those technology challenges, where we are talking about 133 new dishes in the SKA one, and it will incorporate 64 dishes from Meerkat to get to close to 200 dishes. And SKA2 is of course much bigger, and the signal transport rates, the signal processing and the software and the algorithm development and the computing requirements and the data storage, which is again humongous. And finally, last but not the least, is the significant challenge of powering the entire observatory. So I won't go through the details of all of these, just to give you a glimpse, because this is the kind of thing which would be interesting to know from a cosmologist's point of view as to what will be the range of frequencies that it will cover and how the receivers will be configured. And as I said, this it is this part that would be the most interesting for looking at redshifted neutral hydrogen. And both SK low and SK mid therefore will be important in that context. And this just to give you a feel for the kind of complexities in the processing of the data, where the data from each station of SK low is 2 petabits per second and 9 terabits per second from a SK dish, finally ending up into something which is several petaflops of real-time computing to do this, and even then generating petabytes per year of data that would need to be stored, and that itself is a challenge. So the plan is to have regional data centers at different locations in member countries of the SK project, where the SK data would be stored, spread around globally, and also more easy to access for the science community from that particular country. And that of course is a challenge to move the data across the globe to get it from the 2 telescope sites to the different regional centers. So it is really a global partnership with now more than a dozen countries that are involved in working in SK phase 1, others still interested to join, and all of this is now bound by a intergovernmental treaty organization which was created about 3 years ago as one transition from the design phase to the construction phase. And just to give you an overview of where the project stands, like I said, the design phase was completed in March 2020, and the approval by the SKO Council to start construction was in July 2021, and actual work got going towards the end of 2021. So we are already more than a year into the construction phase, and different things are now beginning to happen. The final commitments from different countries to what they are contributing to the project get firmed up as the countries join, and what this does, so the basic issue here is that the total funding committed is not yet equal to the design cost of the facility. So we are at the level of about 80%. So what that 80% allows you to build is what is called a deployment baseline, which is not quite the same as the design baseline. And what that means is that it would get expanded and built up to the complete design baseline with the assumption that more countries would join, or the existing countries would bring in more money as the project proceeds. The good thing about a radio astronomy array is that you can build it up incrementally in this fashion. So this current phase is expected to go until 2027 with phased releases. So you can actually start doing science with, say 20 dishes constructed, and then with 40, and then so on. And that, so that first phase release is expected to be by the end of 2024. And it's expected to be really operational by 2028. And so I'll move to the last part to just talk about what we in India have been doing in terms of participating in the SKA. So we've been part of the SKA since the very beginning. Some of the early concepts of what the SKA should look like actually even originated from India, from our research group by Govind Swarup and team. And over the years, we've been part of the different phases that the SKA went through. And we joined in 2012 with an observer status and transitioned to a full membership in 2015, and participated actively during the design phase of the project. And we've in the time being, we've built up the Indian community interested in SKA, and it now works under the umbrella of the SK India Consortium, which is funded by the DAE. The total Indian contribution in the long term to the SKA is expected to be funded in equal parts by the Department of Atomic Energy DAE and the Department of Science and Technology, the DST, with the DAE being the lead ministry for the SKA project. So this is just an overview of the SK India Consortium, with more than 20 institutions around the country as members, some interested more in the science of the SKA, others interested as well in the technology and the technological developments and being able to contribute to the building of the SKA. And the consortium works on both fronts, science and the technical fronts, with two different subcommittees looking after the growth of the science case in India and the scientific activities, and the other looking after the technical activities and the contribution, in-kind contribution to the building of the SKA. And so during the design phase, we led one of the work packages, the telescope manager, which is one of the critical systems. It's the entire brain and nerve center, provides end-to-end monitoring control for the entire observatory and the complete life cycle management. And so this was something that we worked along with industry partners in India, and as a lead agency for the telescope manager, with members from 6 other SKA countries working in the team. And moving towards the construction phase, we have been identified as a lead country for the actual construction of an enhanced version of the telescope manager, which includes additional functionalities from different subsystems. And we are also part of the SKA low digital signal processing work package, where we hope to build some of the digital signal processing hardware, for which work has already started. And I think if you go to the lab which Prabhu has in the next building, you will actually see some of these prototype boards being worked upon by the team members. There's a copy of this also at the GMRT Observatory, where we are learning how to work with the boards, and eventually we will be building a large number of these in the country, integrating them into the sub-racks and supplying to the SKA low site. So we have other areas of participation at slightly lower levels also, and overall plan is to contribute to the order of somewhere around 6% of the total construction cost of the SKA. In addition to that, our plans include developments that you would want to do in the country, so that you can make this participation a meaningful one. For example, a regional data center is planned to be built in India, and a significant human resource development program is also proposed in our plan, and also an in-house R&D program which would cater to the next generation developments which would be needed for SKA phase 2, for example. So this package of our final plan is in the final stages of review by the Government of India, and we are hoping that we should be able to get the approval to go ahead and become full-fledged members of the SK construction phase in the near future. So I'll stop here. Thank you.
Once again, time for a question. Not seeing one immediate. Oh, go ahead.
Thanks a lot for summarizing both UGMRT and SK India aspect. I was wondering if you could elaborate about the data center in India, like how the SK data is going to be generally divided. Are we going to keep some of the copy, or these are only going to be science analysis data which we are going to host?
Yeah, that's a good question. The full clarity on how that distribution will happen is not yet there. There's work going on to work out a model of how the data would be spread out and shared, and there are different ideas still being talked about. One of them is, the total SKA data resides in pieces in different parts, and as a scientist working on it, you would have the rights to access any of it. There are other things where the countries want preferentially to host data of projects where there is more participation from scientists of that country. So like, for example, if you're a PI on one of the key projects of the SK, you would want that the data center in your country hosts most of that particular kind of data. So these are things that are still being discussed in this. There's a coordination committee for the regional data centers which is trying to thrash out these policy issues and bring them to the council for final approval of how these will be structured.
Thanks. Thanks for the talk, Yashwant. I was just wondering what's next after UGMRT for GMRT.
Okay, so you didn't hear about it in the last few days. Okay, so we ourselves are planning an expansion of the GMRT. Exactly what shape it will take will be known in the next sort of year or so. But the kind of ideas that are being talked about is, of course, to increase the collecting area by adding more dishes. And when the discussion started, there was, well, do we want more long baselines? Do you want more short baselines? But I think the guys with the short baselines are winning that battle for various reasons, which I think is just that sheer collecting area is more important than, say, better angular resolution, or the once wanted dishes out to 80 kilometers and so on. And it's hard to get land and expand outside of the land that you already have. And it also goes the way, for example, SK, the large central core and less number of antennas in the arms. Two, also adding phased array feeds to some, if not all, of the antennas. So likely to double the number of antennas from 30 to 60, to have at least 30 antennas with PAFs, if not 60 antennas with PAFs. So that's in a nutshell the kind of things we are tossing around right now. That proposal is to go to the DAE for funding request within the next 6 months.
So you mentioned that India is hoping to contribute about 6% of the construction cost, I heard. Is there any plan about the operations? Are we
So
going to contribute?
there is as per the charter of the SKO Council, that treaty documents, it says that any country that contributes X percent to the construction cost is expected to contribute X percent of the operation cost. So once you say you're going to contribute 6%, it's expected that you'll pay 6% of the operations cost also, as long as you are members of the treaty.
Okay, you're not seeing any more questions. Let's thank Yashwant and all of the speakers.
So with that, I think just we'll close, and thanks everyone for coming.